Something is pulling you. Right now, as you watch this video, the ground beneath your feet, the planet you call home, the entire Milky Way galaxy, is being dragged through space at 600 kilometers per second toward a place we cannot see. Not pulled by a star, not pulled by a black hole. Pulled by something so massive, so incomprehensibly vast, that it commands the motion of 100,000 galaxies across a region of space 250 million light-years wide. And for decades, we had no idea it was even there. Astronomers call it the Great Attractor. The name sounds dramatic because the reality is dramatic. In 1978, scientists noticed something wrong with the way galaxies were moving. They were drifting, all of them, in the same direction, toward a single point in the southern sky, near the constellation Centaurus. Not scattering outward the way the expanding universe said they should. Converging. Being pulled by a gravitational force so powerful it overrides the Hubble flow itself. The problem was simple and maddening. When they aimed their telescopes at the source, they saw nothing, just stars, dust, the crowded, glowing mess of our own galaxy blocking the view like a curtain drawn across 20% of the observable universe. It would take X-ray telescopes, infrared surveys, and a complete rethinking of what the Great Attractor even is before the truth began to emerge. And that truth is stranger than the mystery. Because the Great Attractor is not what we thought. It is not alone. It is not even the largest thing pulling us. It is one piece of a cosmic architecture so vast that our entire local universe, everything within 500 million light-years, is flowing along highways of gravity we are only now beginning to map. This is that story. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will cross the hidden sky, confront the limits of distance, and ask what it means to measure something without edges. Beyond the darkness lies a moving portrait of home, and a question whose scale may exceed every expectation. The Milky Way is falling, not collapsing, not dying. Falling, moving sideways through space at 600 kilometers per second in a direction it has no obvious reason to be going. For context, that is roughly 2.1 million kilometers per hour. The entire galaxy, every star you have ever seen, every nebula photographed by Hubble, the sun, the planets, this rock you are standing on, all of it hurtling through the void like a marble rolling across a tilted floor, and for decades no one could figure out what was doing the tilting. This is not poetic language. This is not a metaphor for entropy or cosmic loneliness. The Milky Way is being pulled hard by something astronomers spent years trying to see and could not. Something massive enough to drag 100,000 galaxies along with it. Something sitting in the one direction we happen to be facing, where the view is completely blocked. The story starts, as most good cosmic mysteries do, with numbers that refuse to behave. In the early decades of the 20th century, Edwin Hubble figured out that the universe is expanding. Galaxies are moving away from each other in all directions, and the farther away a galaxy is, the faster it recedes. This relationship between distance and velocity is so consistent that it became known as the Hubble flow. It is the baseline rhythm of the cosmos. Everything drifts apart at a predictable rate, carried by the expansion of space itself, except when it doesn't. By the 1970s, astronomers had gotten very good at measuring how fast galaxies were moving. They could look at the light from a distant galaxy, measure how much that light had been redshifted by the Doppler effect, and calculate its velocity with impressive precision. Most galaxies behaved exactly as expected. Their motion matched the Hubble flow. They were coasting along with the expansion, minding their own business, but a few galaxies were not. A small but growing list of nearby galaxies, including our own local group, were moving with what astronomers call a peculiar velocity. That is the technical term, and it means exactly what it sounds like. A peculiar velocity is the component of a galaxy's motion that cannot be explained by the expansion of the universe. It is the leftover, the drift, the thing pulling or pushing a galaxy off the script. The local group, for those keeping track, is the gravitationally bound cluster of galaxies that includes the Milky Way, Andromeda, the Triangulum galaxy, and about 50 smaller satellite galaxies. This is our immediate neighborhood. And by the late 1970s, it was becoming clear that the entire neighborhood was drifting in the same direction, not toward Andromeda, not toward the center of mass of the local group, toward something else. Something far away, somewhere in the southern sky, in the direction of the constellations Hydra and Centaurus. At first, this was treated as a curiosity. Galaxies tug on each other all the time. Gravity does not turn off just because space is expanding. If a massive cluster of galaxies happened to be sitting in that direction, it would make sense for us to be drifting toward it. The math was straightforward. Find the cluster, measure its mass, confirm it matches the observed motion. Problem solved. They found clusters, lots of them. The Hydra-Centaurus supercluster sits in that general direction, a sprawling collection of thousands of galaxies spread across tens of millions of light-years. But when astronomers added up the mass, it was not enough, not even close. The clusters they could see were pulling on us, sure, but the strength of the tug did not match the speed we were moving. It was like watching a car accelerate down a hill and then realizing the hill is not steep enough to explain the speed. So they kept looking. They measured more galaxies. They refined the distance estimates. They double-checked the velocity measurements. And the more carefully they looked, the worse the problem became, because it was not just the local group that was drifting. It was thousands of galaxies across hundreds of millions of light-years, all moving in the same direction, all being pulled toward the same patch of sky. In 1986, a team of astronomers published a paper that made the problem official. The group, which included Donald Lyndon Bell, Sandra Faber, and several others, analyzed the distances and velocities of roughly 400 elliptical galaxies scattered across the nearby universe. They used a technique called the Tully-Fisher relation, which links a galaxy's rotation speed to its intrinsic brightness. Measure how fast a galaxy spins, calculate how bright it should be, compare that to how bright it looks from Earth, and you have a distance. When they plotted the results, the pattern was undeniable. The galaxies were not just drifting, they were streaming, flowing like water toward a drain, and the drain was sitting in a region of sky that, by cosmic bad luck, happened to be almost completely hidden from view. They called it the Great Attractor. The name stuck because it did exactly what a good name is supposed to do. It captured the mystery and made it sound like something out of science fiction, which, at the time, it might as well have been, because no one had actually seen the thing. No telescope had pointed at it and found a giant glowing sign that said, "Here is the source of all this motion." The Great Attractor was inferred, a ghost in the data, a conclusion drawn from watching galaxies move in ways they should not be moving unless something enormous was pulling them. The initial estimates were staggering. To produce the observed motion across such a large region, the Great Attractor would need to contain a mass equivalent to tens of thousands of Milky Way-sized galaxies. Some early papers suggested it might be the largest concentration of mass in the nearby universe, a kind of gravitational anchor holding down an entire corner of the cosmic web. And it was sitting behind the Milky Way. This is where the frustration really set in. Because the direction the galaxies were streaming toward, the exact spot where the Great Attractor was supposed to be, lies almost directly behind the plane of our own galaxy. When you look at the Milky Way from Earth, you are looking edge-on through the flat disk of stars, gas and dust that makes up the galaxy's main body. That disk is not transparent. It is packed with material that absorbs and scatters light, especially in the visible spectrum. Astronomers call this region the zone of avoidance. It is not a physical barrier. It is just the unfortunate fact that if you want to see what is behind your own galaxy, you have to look through your own galaxy first, and your own galaxy is in the way. For optical telescopes, the zone of avoidance is a dead zone. You can point a telescope at it, expose for hours, and still see almost nothing beyond the foreground stars and dust clouds cluttering up the view. It is like trying to watch a football game through a chain-link fence covered in ivy. You know something is happening back there. You just cannot see it. The Great Attractor was hiding in plain sight. Or rather, it was hiding in no sight at all. To make matters worse, the region in question is in the southern sky, which meant that many of the world's most powerful telescopes, located in the northern hemisphere, could not even point at it properly. For decades, the tools astronomers needed to solve the mystery were either blocked by the Milky Way's disk or sitting on the wrong side of the planet. The only information they had to work with was indirect, velocity measurements from galaxies scattered around the region, distance estimates from redshift surveys, gravitational models built on incomplete data. It was like trying to map a mountain range by listening to the echoes and guessing where the peaks should be. Still, the picture that emerged from those early studies was consistent. Something big was out there, something with enough mass to pull not just the Milky Way, but the entire local group, the Virgo cluster, and thousands of other galaxies into a coherent flow. The center of that flow appeared to be located somewhere between 150 and 250 million light-years away, depending on which paper you read and which method they use to calculate the distance. For scale, the nearest large galaxy to the Milky Way, Andromeda, sits about 2.5 million light-years away. The Virgo cluster, one of the largest structures in our cosmic neighborhood, is roughly 50 to 60 million light-years distant. The Great Attractor, by comparison, was sitting at a distance 3 or 4 times farther than Virgo and pulling on us harder than anything closer. That should not be possible. Gravity falls off with distance. The farther away a mass is, the weaker its pull. For something that far away to dominate the motion of our local patch of the universe, it would need to be unimaginably massive, not just a large galaxy, not just a cluster. A supercluster, a concentration of mass so enormous that it bent the trajectories of galaxies across hundreds of millions of light-years, like marbles rolling toward the bottom of a bowl. And yet, no one could see it. The Great Attractor hypothesis had a second problem beyond visibility. Even if astronomers could peer through the zone of avoidance and locate the source, they were not entirely sure what they were looking for. Was it a single enormous galaxy cluster sitting at the focal point? Was it a chain of clusters lined up along our line of sight, collectively producing the observed pull? Was it something even stranger, a dark concentration of mass with no visible counterpart at all? The term Great Attractor itself was both a placeholder and a provocation. It named the mystery without solving it. And for a solid decade, that was where things stood. 100,000 galaxies streaming toward an invisible point in space. A ghost behind the Milky Way, pulling harder than anything we could see. By the early 1990s, astronomers had started calling it the Great Attractor problem. Not because they doubted the measurements. The velocities were real, the motion was real. The problem was explaining what could produce that motion without violating the basic rules of how structure forms in an expanding universe. The standard model of cosmology, the framework that describes how galaxies and clusters assemble over billions of years, relies on a process called hierarchical clustering. Small overdensities in the early universe pull in surrounding matter through gravity. Those overdensities grow into larger clumps. Those clumps merge into clusters. Clusters merge into superclusters. The whole process takes time, billions of years. And the structures it produces are supposed to be spread out, diffuse, organized into filaments and sheets that stretch across hundreds of millions of light years. What the Great Attractor data seemed to suggest was something different. A single dominant concentration of mass sitting at the center of a vast streaming flow. That kind of configuration does not emerge naturally from hierarchical clustering unless something unusual happened. Either the initial conditions in that region of space were anomalous, seeding a much larger overdensity than average, or the region had undergone an unusually efficient collapse, funneling matter inward faster and more completely than the standard model predicts. Neither explanation was satisfying. Both required fine-tuning the initial conditions of the universe in ways that felt arbitrary, and neither could be tested without actually seeing the thing. The frustration was methodological as much as observational. Astronomy is a field built on looking at things. You point a telescope at an object, collect its light, measure its properties, and draw conclusions. The Great Attractor flipped that process on its head. Astronomers were being asked to study something they could not observe directly, to infer its properties from the behavior of objects nearby, to build a model of a mountain by watching rivers flow downhill. It worked, in the sense that the models produced numbers that matched the observations, but it did not feel like understanding. It felt like guessing. There was also a lingering philosophical discomfort. The universe is not supposed to have a center. That is one of the core principles of modern cosmology. The Big Bang did not happen at a point in space and then expand outward. It happened everywhere at once. Every point in space is equivalent. There is no preferred location, no cosmic downtown, no place where the universe is more universe than anywhere else. And yet here was a region of space that seemed to be acting like a center, a gravitational hub, pulling everything nearby toward it. A place where the normal rules of cosmic expansion were being overruled by something local and massive. It was not a violation of cosmology, exactly. Gravity is allowed to clump matter into structures. That is how galaxies form in the first place. But the scale of the effect was uncomfortable. It suggested that on scales of hundreds of millions of light years, the universe was lumpier than anyone had expected. The Great Attractor was not just a mystery, it was a challenge, a reminder that the universe does not owe us visibility, that the most important things can be hidden in the places we cannot see. That sometimes the only way to know something is there is to watch everything around it move in ways that make no sense unless it exists. And so, for years, astronomers watched. They catalogued more galaxies, they refined the velocity measurements, they built better models. They argued about what the data meant, and all the while, the Milky Way kept falling, pulled by a force no one could see, toward a destination hidden just out of reach behind the glare and dust of our own galaxy's disk. The problem with trying to see the Great Attractor was not just that it was far away. Distance is a challenge astronomers deal with every night. They have gotten very good at it. Build a bigger mirror, collect more photons, integrate the signal over longer exposures, and eventually even the faintest objects give themselves away. The problem with the Great Attractor was not distance, it was location. It was sitting behind the worst possible obstruction in the entire sky. Our own galaxy. The Milky Way, seen from Earth, is not a distant object you observe through a telescope. It is the thing you are standing inside. A flat rotating disk of stars, gas and dust, roughly 100,000 light-years across and about 1,000 light-years thick. When you look up at night and see that pale band of light stretching from horizon to horizon, you are looking edge-on through that disk. You are seeing the combined glow of billions of stars, too faint and too far to resolve individually, smeared together into a continuous haze. It is beautiful. It is also in the way. When astronomers try to observe galaxies beyond the Milky Way, they are looking through all the material packed into our own galactic plane. Stars, clouds of hydrogen and helium, dust grains made of carbon and silicates, molecules of water and carbon monoxide, entire nebulas glowing with ionized gas, all of it sitting between the telescope and whatever lies beyond, and all of it scattering, absorbing and blocking the light trying to pass through. This is not a small inconvenience. It is a fundamental observational barrier, and the region of sky where it hits hardest has a name. Astronomers call it the zone of avoidance. The term is not poetic. It is descriptive. For decades, if you were an astronomer trying to map the large-scale structure of the universe, you avoided that zone. You pointed your telescope anywhere else, because trying to see through the galactic plane was like trying to read a book through frosted glass smeared with mud. Technically possible if you squint hard enough and make enough assumptions, practically useless if you want reliable data. The zone of avoidance spans roughly 20% of the sky. It is not a sharp boundary. The obscuration fades gradually as you move away from the galactic equator, the imaginary line that traces the midplane of the Milky Way's disk. Near the equator, the extinction, the technical term for how much light gets blocked, can reach several magnitudes in the visible spectrum. That means a galaxy that would appear bright and obvious if it were located in a clear part of the sky becomes 10, 100, even 1,000 times dimmer when viewed through the disk. Many simply disappear from view entirely. Dust is the primary culprit. Interstellar dust is not the kind of dust you find under your couch. It is made of tiny solid grains, most of them smaller than the wavelength of visible light, composed of carbon, silicon, oxygen, and trace metals. These grains form in the outer atmospheres of dying stars, get blown into space by stellar winds and supernova explosions, and collect in the cooler regions of the galaxy where they can clump together into clouds. Dust does two things that make life difficult for astronomers. First, it absorbs light, particularly at shorter wavelengths. Blue light gets blocked more efficiently than red light, which is why objects viewed through a dusty region often appear redder than they actually are. This effect is called reddening, and it is one of the most annoying sources of systematic error in observational astronomy because it mimics the redshift caused by cosmological expansion. A galaxy that looks red because it is moving away from us at high speed looks almost identical to a galaxy that looks red because there is dust in the way. Disentangling the two requires careful calibration and a lot of cross-checking. Second, dust scatters light. When a photon traveling through space hits a dust grain, it can bounce off in a random direction. Most of those scattered photons never make it to the telescope. The result is that the image of any object behind the dust becomes fainter and blurrier. Fine details wash out. Faint sources vanish. The deeper you try to look through a dusty region, the worse it gets. Gas adds to the problem, though in a different way. The Milky Way's disk is full of hydrogen, the most abundant element in the universe. Most of that hydrogen is neutral, meaning it has not been ionized by nearby stars. Neutral hydrogen does not emit much visible light, which makes it nearly invisible to optical telescopes. But it is there, and it has mass, and when light from a distant galaxy tries to pass through a cloud of neutral hydrogen, the gas can absorb specific wavelengths corresponding to the hydrogen atom's energy levels. The most famous of these is the 21-centimeter line, a radio wavelength that hydrogen emits and absorbs naturally. For radio astronomers, this is extremely useful. For anyone trying to build a clean optical image of something behind the gas, it is one more layer of interference. Then there are the stars themselves. The galactic plane is crowded. When you point a telescope at a region near the Milky Way's equator, the field of view is packed with foreground stars from our own galaxy, thousands of them in a single image, depending on the instrument and the exposure time. Each one of those stars contributes light that has nothing to do with the distant background galaxies you are trying to study. The stars are bright, the galaxies are faint. Separating signal from noise becomes a statistical nightmare. Modern image processing can subtract out most of the foreground stars if you are patient and methodical, but it is not perfect. Stars have diffraction spikes, optical artifacts caused by the way light bends around the supports holding a telescope's secondary mirror. They have halos, faint glows caused by imperfect focus or scattered light inside the instrument. If a faint background galaxy happens to sit right next to a bright foreground star, good luck extracting a clean measurement. You can try. You will spend hours tweaking the background subtraction algorithm and second-guessing every pixel. And at the end of it all, you still will not be sure if what you are seeing is real or just noise dressed up as a signal. The zone of avoidance is not a uniform barrier. Some lines of sight through the galactic plane are worse than others. Regions where the disk is thicker, where star formation is active, where dust clouds are densest, those regions are effectively opaque. Other regions, where the disk thins out, or where gaps in the dust distribution happen to align with our line of sight, offer narrow windows through which you can catch glimpses of the universe beyond. Astronomers call these windows, and they are some of the most heavily observed patches of sky in the entire zone of avoidance. Not because they are intrinsically interesting, but because they are the only places you can see anything at all. For most of the 20th century, the zone of avoidance was simply written off. Galaxy surveys swept across the sky, cataloging tens of thousands of objects, and when they reached the galactic plane, they stopped. The maps of the universe compiled from those surveys had a giant blank stripe running through them, a data gap that everyone knew was there and nobody could fill. It was frustrating, but it was accepted. Some problems do not have solutions. You work around them. The Great Attractor made that approach untenable. Because the region where galaxies were streaming, the focal point of the largest coherent flow of matter in the nearby universe, was sitting right in the middle of that blank stripe, not near it, not adjacent to it, dead center, in one of the most obscured regions of the entire zone of avoidance. If you wanted to understand what was pulling 100,000 galaxies, you had to look in the one direction where looking was nearly impossible. So astronomers did what they always do when visible light fails them. They stopped using visible light. Infrared observations were the first breakthrough. Infrared light has longer wavelengths than visible light, which means it passes through dust much more easily. A dust cloud that completely blocks blue and green light might be nearly transparent to infrared. The trade-off is that infrared instruments are harder to build and operate. Infrared detectors have to be cooled to extremely low temperatures to avoid being blinded by their own thermal radiation. The Earth's atmosphere absorbs most infrared wavelengths, so you either need to put your telescope on a mountaintop where the air is thin and dry, or you need to put it in space. Both options are expensive. By the late 1980s and early 1990s, space-based infrared telescopes like the Infrared Astronomical Satellite, known as IRS, and later the 2-micron all-sky survey, called 2MASS, began mapping the sky at wavelengths where dust is less of a problem. These surveys could see through much of the zone of avoidance and detect galaxies that had been completely invisible to optical telescopes. The maps they produced were revolutionary. For the first time, astronomers could begin to fill in the blank stripe. What they found was structure, lots of it. clusters of galaxies, filaments of galaxies, entire superclusters that had been hidden from view. The universe behind the Milky Way was not empty, it was full, and some of the largest concentrations of mass in the nearby universe were sitting in regions that had been total blind spots for decades. Radio astronomy helped too. Neutral hydrogen, the same gas that complicates optical observations, emits that 21-centimeter line, and radio telescopes can detect it across enormous distances. By mapping the distribution of hydrogen in and around galaxies near the zone of avoidance, astronomers could identify objects that were too faint or too obscured to show up in optical surveys. The hydrogen signal does not care about dust. It passes right through. Radio surveys added thousands of new galaxies to the catalogue, many of them sitting in regions where optical telescopes saw nothing but foreground stars and murk. X-ray observations turned out to be even more useful. Galaxy clusters, the largest gravitationally bound structures in the universe, contain enormous amounts of hot gas trapped in the gravitational wells of their combined mass. That gas is heated to tens of millions of degrees by the energy of galaxies moving through it and by the gravitational collapse of the cluster itself. At those temperatures, the gas emits X-rays. And X-rays, like infrared and radio waves, are not significantly absorbed by the dust and gas in the Milky Way's disk. An X-ray telescope can see through the zone of avoidance almost as if it were not there. In the early 2000s, a survey called the Clusters in the Zone of Avoidance Project, abbreviated CESA, used X-ray data to map galaxy clusters hidden behind the Milky Way. The results were stunning. The survey identified several massive clusters sitting in regions that had been nearly blank on earlier maps. One of them, a cluster in the constellation Norma, turned out to be one of the most massive clusters in the nearby universe. And it was sitting almost exactly where the galaxy velocity data predicted the Great Attractor should be. That cluster, the Norma cluster, became the leading candidate for the long-sought source of the Great Attractor's pull. But identifying it required looking through the most obscured part of the entire zone of avoidance. Without X-ray astronomy, it might never have been found. Even with all these new tools, working in the zone of avoidance is hard. The observations are always noisier than they would be in a clear part of the sky. The uncertainties are always larger. You cannot just point a telescope, take a picture, and trust what you see. Every measurement has to be cross-checked against multiple wavelengths. Every detection has to be confirmed with follow-up observations. And even then, there are objects you simply miss because they are too faint, too obscured, or too unlucky in their placement relative to foreground stars. The deeper issue is that the zone of avoidance creates a fundamental selection bias in our maps of the universe. When you survey the sky and catalogue galaxies, your sample is only as good as your ability to detect things. If an entire region of sky is systematically harder to observe, you will find fewer galaxies in that region, not because there are fewer galaxies there, but because you cannot see them. The result is that any large-scale structure that happens to lie behind the galactic plane will appear fainter, less massive, and less significant than it actually is. You will underestimate its importance. You will draw conclusions about the universe that are skewed by the accident of where you happen to be standing. For decades, that is exactly what happened with the Great Attractor. The velocity data said there was something enormous pulling on us. But the galaxy counts in that direction did not show anything unusual. The region looked underpopulated. Some astronomers speculated that maybe the Great Attractor was not a visible structure at all. Maybe it was a concentration of dark matter with no galaxies attached. Maybe it was an artifact of the velocity measurement method. Maybe the whole idea was wrong. It was not wrong. The structure was there. It was just hidden. The frustration was methodological. Astronomy is built on the assumption that if you look carefully enough, you will see what is there. The zone of avoidance broke that assumption. It forced astronomers to study a region of the universe indirectly, using proxies and workarounds and instruments that could pierce the veil their own galaxy had draped across the sky. It was like trying to map the layout of a city by listening to traffic sounds through a thick wall. You can infer a lot, you can build a rough picture, but you are always working with incomplete information, and you are always aware that something important might be hiding just out of reach. The zone of avoidance also highlighted a broader truth about astronomy. The universe does not arrange itself for our convenience. The most important structures are not always the easiest to see. Sometimes the thing you are looking for is sitting in the worst possible location, obscured by the one object you cannot move out of the way, your own galaxy. By the early 2000s, after more than a decade of infrared, radio, and X-ray surveys, astronomers had finally assembled a rough map of the region behind the zone of avoidance. It was incomplete, it was uncertain, but it was enough to start testing the Great Attractor hypothesis properly. And what they found was both a confirmation and a complication. There was structure there, massive structure, but it was not quite what anyone had expected. The Norma cluster sat near the center of the predicted location, and it was enormous. Thousands of galaxies packed into a region a few tens of millions of light-years across, with a combined mass on the order of 10 to the 15th solar masses. That is a lot of mass, enough to produce a significant gravitational pull on nearby galaxies. But when astronomers ran the numbers, they found that the Norma cluster alone could not explain the full magnitude of the motion. The velocity field was too strong, too coherent, too widespread. There had to be more, and there was. The Norma cluster turned out to be just one piece of a much larger structure, a supercluster. A sprawling network of galaxy clusters, filaments, and smaller groups, all linked together by gravity and stretching across hundreds of millions of light-years. The Great Attractor was not a single object, it was a region. A gravitational knot in the cosmic web, where an unusually large amount of matter had collected over billions of years. That realization shifted the entire conversation. The question was no longer, what is the Great Attractor? The question became, how does this region fit into the larger structure of the universe? And that question required looking beyond the zone of avoidance, beyond the nearby galaxy clusters, out into the deeper cosmic web, where the motions of galaxies are shaped not by one attractor, but by many. The zone of avoidance had hidden the answer for decades. But once astronomers figured out how to see through it, the picture that emerged was bigger and stranger than anyone had guessed. The Milky Way was not just falling toward a single cluster, it was riding a wave. A vast streaming motion shaped by the uneven distribution of matter across hundreds of millions of light-years, and the Great Attractor, the ghost that had haunted galaxy surveys for so long, was just one node in a much larger network. But to see that network, to map the full shape of the flow, astronomers needed more than infrared telescopes and X-ray surveys. They needed a new way of thinking about motion and structure. They needed to stop asking where galaxies are and start asking where they are going. That shift in perspective, combined with decades of patient observation through the most obscured regions of the sky, would eventually reveal the true scale of what was pulling us. And the answer was far larger than the Great Attractor had ever been. The breakthrough started with a gamble and a telescope that was never supposed to change cosmology. In the early 1990s, a team of astronomers decided to do something that most of their colleagues considered a waste of valuable observing time. They pointed an infrared detector at one of the most obscured regions of the zone of avoidance and started collecting photons. Not because they expected to find anything spectacular, because they had run out of excuses not to look. The technology had finally caught up to the problem. Infrared astronomy, once an exotic specialty requiring liquid helium-cooled detectors and observatories perched on remote mountaintops, had become routine enough that teams could justify devoting serious time to mapping regions of sky that optical telescopes had written off as hopeless. The surveys had names that sounded like government agencies. IRAS, the Infrared Astronomical Satellite, launched in 1983. 2MASS, the 2-micron All-Sky Survey, which began operations in the late 90s. DINIS, the Deep Near-Infrared Survey of the Southern Sky. Each one adding layers of data, filling in gaps, revealing structure that had been invisible for decades. What they found in the direction of the Great Attractor was not a void, it was a crowd. The first detections were tentative, smudges on images, faint sources barely distinguishing themselves from the noise. You had to squint at the data and convince yourself that what you were seeing was real and not just an artifact of the background subtraction algorithm. But as more observations accumulated, the smudges resolved into galaxies, dozens of them, then hundreds, packed into a region that optical surveys had shown as nearly empty. The densest concentration sat in the constellation Norma, a faint and unremarkable patch of southern sky that most amateur astronomers could not locate without a star chart. Norma is not a prominent constellation. It does not have bright stars or memorable patterns. It sits low on the horizon for Northern Hemisphere observers, and even for those in the Southern Hemisphere, it is overshadowed by its neighbors, Scorpius and Centaurus. Norma is the kind of constellation that exists primarily to fill space on a map, a placeholder, and sitting behind it, hidden by the Milky Way's disk, was one of the most massive galaxy clusters in the nearby universe. They called it the Norma cluster, and it took years to understand what they were looking at, because the cluster was not just obscured by dust. It was sitting in a region of sky so crowded with foreground stars that early images looked like someone had spilled glitter on top of a photograph. Every patch of darkness between the stars contained galaxies, but separating the signal from the clutter required patience, cross-referencing, and an almost obsessive attention to detail. The first comprehensive study of the Norma cluster came in the mid-1990s, led by a team that included René Kraan-Korteweg, a Dutch astronomer who had spent much of her career working on the zone of avoidance problem. Kraan-Korteweg and her colleagues used a combination of optical, infrared, and radio observations to piece together a catalogue of galaxies in the region. What emerged from that work was a picture of a cluster sitting almost exactly where the Great Attractor's center of mass had been predicted to lie. The numbers were staggering. The Norma cluster contained thousands of galaxies. The exact count depended on where you drew the boundary and what you counted as a member versus a foreground or background object. But conservative estimates put the total at several thousand. The cluster's core was packed with giant elliptical galaxies, the kind of massive, old red galaxies that dominate the centers of rich clusters. Surrounding the core were spiral galaxies, irregular galaxies, dwarf galaxies, all bound together by gravity into a single coherent structure. The cluster's total mass was harder to pin down, but the estimates that started appearing in papers in the late 90s suggested something on the order of 10 to the 15th solar masses. That is a 1 followed by 15 zeros, 1,000 trillion times the mass of the Sun. For comparison, the Milky Way weighs in at roughly 600 billion solar masses. The Norma cluster contained enough mass to account for more than 1,000 Milky Way-sized galaxies, even though many of its member galaxies were smaller. The bulk of the mass was not in stars. It was in dark matter, the invisible gravitational scaffolding that holds clusters together and outweighs visible matter by a factor of 5 or 6 to 1. Finding a cluster that massive was exciting. Finding it in the exact direction where galaxies were streaming was more than exciting. It was a confirmation. For more than a decade, the Great Attractor had been a hypothesis, a ghost inferred from velocity measurements. Now there was a physical object sitting at the coordinates. A real concentration of galaxies and dark matter with enough gravitational pull to affect the motion of everything nearby. The Norma cluster looked like the answer. Astronomers ran the numbers. They modeled the cluster's gravitational field. They calculated how much mass you would need to produce the observed streaming velocities across the surrounding region. The match was close. Not perfect, but close enough that many researchers began referring to the Norma cluster as the Great Attractor. The two names became nearly synonymous in the literature. Papers published in the late 90s and early 2000s often used them interchangeably, as if the mystery had been solved and all that remained was to fill in the details. The details, as it turned out, were where the problems started. The streaming motion of galaxies toward the Great Attractor extended across a volume of space roughly 300 million light-years across. That is an enormous region. The velocity field was coherent across that entire volume, meaning galaxies on opposite sides of the flow were all moving in the same general direction. That kind of large-scale coherence is not easy to produce. Gravity falls off with distance. A single massive cluster can pull on nearby galaxies with considerable force. But the farther you get from the cluster, the weaker the pull becomes. By the time you reach distances of 100 million light-years or more, the gravitational influence of even the most massive cluster should be diluted to the point where it is barely noticeable. The Norma cluster sits roughly 200 million light-years from the Milky Way, depending on which distance estimate you trust. That is close enough to produce a measurable pull. But the galaxies streaming toward the Great Attractor were not just near the Milky Way. They were scattered across hundreds of millions of light-years, some of them much closer to the Norma cluster than we are, others much farther away. For the Norma cluster alone to explain the motion of all those galaxies, its gravitational influence would need to reach farther and pull harder than any single cluster should be able to. Astronomers tried to make the numbers work. They adjusted the mass estimates. They tweaked the models. They added more dark matter. The models could reproduce the general pattern of the flow, but they always came up short when you looked at the details. The velocities in the outer regions were too high. The coherence of the motion was too strong. Something was missing. The obvious answer was that there was more mass in the region than the Norma cluster alone, and there was. As infrared and radio surveys continued to map the zone of avoidance, they found additional clusters, smaller groups, filaments of galaxies, all sitting in the same general area. The Great Attractor was not a single cluster, it was a supercluster, a sprawling network of gravitationally linked structures stretching across a couple 100 million light-years. The Norma cluster was the largest single concentration, the densest knot in the web, but it was not alone. That should have solved the problem. Add up the mass of all the clusters and groups in the region, model their combined gravitational field, and the numbers should match the observations. They did, mostly. The match was better than it had been with the Norma cluster alone. But it was still not perfect. The streaming motion extended farther and involved more galaxies than even a supercluster the size of the Great Attractor region could fully explain. There was also a second issue that had been lurking in the background since the beginning: the direction of the flow. Galaxies were streaming toward the Great Attractor, yes, but they were not streaming directly toward it. The velocity vectors, the arrows showing which way galaxies were moving, pointed toward the Norma cluster, but they also pointed slightly past it, as if the galaxies were being pulled not just toward the cluster, but through it, toward something beyond. That observation had been noted in several early papers, but it had not been taken seriously because the uncertainties in the velocity measurements were large enough that you could explain it away as noise. Maybe the flow was aimed directly at the Norma cluster, and the offset was just a measurement artifact. Maybe individual galaxies had their own random motions that blurred the average direction of the flow. Maybe the models were missing some detail about how clusters gravitationally interact with passing galaxies. Or maybe the Great Attractor was not the final destination. The possibility that the flow extended beyond the Great Attractor region started gaining traction in the early 2000s, driven by better velocity surveys and more complete maps of the galaxy distribution. One of the key pieces of evidence came from the discovery of an even larger structure farther out in the same general direction. The Shapley Supercluster, named after Harlow Shapley, the astronomer who first identified it in the 1930s, sits roughly 600 million light-years from Earth, about 3 times farther than the Great Attractor. The Shapley Supercluster is one of the most massive structures in the observable universe. It contains more than 8,000 galaxies and has a total mass estimated at roughly 10 to the 16th solar masses. That is 10 times the mass of the Norma cluster. 10 times. If you wanted to find something with enough gravitational pull to explain a streaming motion that extends across hundreds of millions of light-years, Shapley is a much better candidate than anything in the Great Attractor region. The problem was distance. Shapley is so far away that its gravitational influence on the Milky Way and other nearby galaxies should be weak. Gravity falls off as 1 over distance squared, double the distance, and the force drops by a factor of 4, triple the distance, and it drops by a factor of 9. Shapley is 3 times farther than the Great Attractor. Its pull on us should be 9 times weaker. Even accounting for its much larger mass, the math suggested that Shapley's contribution to our motion should be smaller than the Great Attractor's, not larger. Unless the Great Attractor was not the only thing pulling us, unless the motion we observe is the result of multiple attractors, each contributing to a complex flow pattern that cannot be explained by looking at any single object in isolation. That idea, that galaxy motions are shaped by the combined gravitational influence of all the mass in a large region rather than by one dominant attractor, had been proposed before. But proving it required mapping the velocity field across enormous volumes of space with enough precision to disentangle the individual contributions. That kind of survey was not possible in the 1990s. By the 2000s, it was starting to become feasible. The Norma cluster, in this emerging picture, was not the Great Attractor. It was a landmark. A massive concentration of galaxies sitting near the center of a much larger gravitational basin. The basin itself, the region where galaxies were being pulled inward from all directions, was what deserved the name Great Attractor. The Norma cluster was the biggest single object inside that basin, but it was not the source of the pull. It was just one piece of a distributed mass that collectively shaped the flow. This realization was both satisfying and frustrating. Satisfying because it explained why the Norma cluster alone had never quite accounted for the full motion. Frustrating because it meant the Great Attractor was not a thing you could point a telescope at and say, there it is. It was a region, a gravitational effect spread across hundreds of millions of light-years with no single center. The Norma cluster was the heart of the attractor, only in the sense that it sat near the middle of the region and contained more mass than anything else nearby. But calling it the heart implied it was the engine driving the motion, and it was not. The shift in understanding was gradual. Papers published in the late 2000s and early 2010s started referring to the Great Attractor as a region rather than an object. The Norma cluster was still important, still the most prominent feature in that region, but it was no longer treated as synonymous with the attractor itself. The terminology got messier. Some astronomers kept using Great Attractor to refer specifically to the Norma cluster. Others used it to mean the entire supercluster. Still others dropped the term altogether in favor of more precise names like the Norma Cluster or the Centaurus Supercluster or the Great Attractor overdensity. The confusion was not just semantic. It reflected a deeper ambiguity about what the Great Attractor actually was. The original definition, the thing pulling 100,000 galaxies into a coherent flow, was clear. But as observations improved and the picture got more complex, that definition became harder to pin down. Was the pull coming from one supercluster, from multiple superclusters, from the entire network of filaments and clusters that filled the region? Where did the Great Attractor end and the rest of the universe begin? Those questions did not have clean answers. The universe does not come with boundary lines. Structures blend into each other. Clusters merge into superclusters. Superclusters connect along filaments. The idea that you could identify a single region and call it the Great Attractor started to seem arbitrary. Useful as a shorthand, maybe, but not a fundamental description of what was happening. The Norma Cluster remained the best observed and most thoroughly studied part of the Great Attractor region. As infrared and radio surveys improved, astronomers catalogued more and more of its member galaxies. They measured redshifts, calculated masses, mapped the distribution of dark matter using gravitational lensing. The cluster became one of the most important laboratories for studying how massive structures form and evolve in the universe. But it also became clear that the Norma Cluster was not unique. It was not the only massive cluster hidden behind the zone of avoidance. Surveys in the 2000s found additional clusters in adjacent regions of sky, some of them nearly as massive as Norma, all of them contributing to the overall mass distribution in the Great Attractor area. The picture that emerged was not of a single dominant object, but of a complex overdensity with multiple peaks, multiple concentrations of mass, all linked together into a coherent structure by the gravity that bound them. Calling the Norma Cluster the heart of the attractor was not wrong, exactly. It was the densest, most massive part of the region. It sat near the center of the velocity flow. It was the first piece of the puzzle that astronomers could actually see and study in detail. In that sense, it deserved the title. But hearts pump. They drive circulation. They are the engine. The Norma Cluster was not driving the flow. It was part of it, a participant, not a prime mover. The real driver, the thing that was pulling galaxies from hundreds of millions of light years away, was the combined mass of everything in the region. The Norma Cluster, the surrounding clusters, the filaments connecting them, the dark matter halos that extended far beyond the visible galaxies, all of it together, distributed across an enormous volume, collectively warping space and shaping the motion of everything nearby. That was the Great Attractor. Not a place you could visit, not an object you could photograph, a gravitational basin, a dip in the fabric of space-time caused by an unusual concentration of mass in one corner of the universe. The discovery of the Norma Cluster had been the breakthrough that turned the Great Attractor from a hypothesis into something observable. It proved that the mass was there. It showed that the zone of avoidance had been hiding an enormous structure that previous surveys had missed. It gave astronomers a target, a physical location where they could point their telescopes and start answering questions. But it also raised new questions that were harder to answer. How much mass was really in the region? How was it distributed? How did the Great Attractor fit into the larger structure of the universe? And why, after all the effort spent mapping the Norma Cluster and the surrounding area, did the streaming motion still extend farther than the models predicted? The answers to those questions required looking beyond infrared surveys. Infrared could see through the dust. It could reveal galaxies hidden behind the zone of avoidance, but it could not see everything. It could not map the hot gas filling the space between galaxies. It could not trace the shock fronts and turbulence left behind by clusters colliding and merging. It could not detect the signatures of active supermassive black holes feeding at the centers of galaxies. For that, astronomers needed a different kind of light. They needed X-rays. The Norma cluster had given astronomers something they desperately needed: a target, a physical object sitting in the zone of avoidance that matched, at least approximately, the location where the Great Attractor was supposed to be. But even as infrared surveys filled in the map of that region, even as radio observations added thousands of new galaxies to the catalogue, the picture remained frustratingly incomplete, because there was a limit to what infrared and radio could tell you. They could show you where the galaxies were. They could measure how fast those galaxies were moving, but they could not show you what was happening in the space between the galaxies. And in a massive galaxy cluster, the space between is where most of the action is. Galaxy clusters are not just collections of galaxies sitting near each other. They are gravitational prisons. Thousands of galaxies bound together by their combined mass, orbiting through a shared gravitational well at speeds of hundreds or thousands of kilometers per second. When galaxies move that fast through a confined region, they collide. Not in the Hollywood sense where everything explodes. Galaxy collisions are gentle by human standards because galaxies are mostly empty space. The stars pass through each other like two swarms of gnats, interpenetrating without a single individual impact. But the gas does not pass through. Gas collides. And when gas moving at 1,000 kilometers per second slams into more gas moving at 1,000 kilometers per second in the opposite direction, it heats up. The temperature it reaches is absurd, tens of millions of degrees Kelvin, hot enough to strip electrons from atoms, hot enough to ionize anything. At those temperatures, the gas does not glow in visible light. It does not glow in infrared. It glows in X-rays. And if you want to see what a galaxy cluster is actually doing, if you want to map the distribution of mass, trace the history of collisions and mergers, understand how much material is really there, you need to look at the X-rays. The problem with X-ray astronomy is that you cannot do it from the ground. Earth's atmosphere absorbs X-rays completely. That is a good thing if you are a human who enjoys not being sterilized by solar radiation. It is a bad thing if you are an astronomer trying to map the hot gas in distant galaxy clusters. To observe X-rays from space, you need to put your telescope in space. And for most of the 20th century, space telescopes were expensive, difficult to build, and limited in what they could observe. The first X-ray satellites were small, crude instruments that could detect bright sources, but could not image them with any useful resolution. They proved that the universe was full of X-ray emitting objects, supernova remnants, black holes feeding on nearby stars, the hot coronas of active stars, and clusters, lots of clusters. By the late 1970s, it was clear that galaxy clusters were among the brightest X-ray sources in the sky. But mapping them in detail, building a complete picture of where the hot gas was and how it was distributed, required better instruments. The breakthrough came in the early 1990s with the launch of ROSAT, the Röntgen satellite, a joint project involving Germany, the United States, and the United Kingdom. ROSAT carried an X-ray telescope with imaging capabilities far beyond anything that had flown before. It could resolve structure, it could map extended sources, it could take a blurry glow in the sky and turn it into a picture with enough detail that you could see the shape of the cluster, identify substructure, trace where the gas was dense and where it was thin. ROSAT launched in June of 1990 and spent the next 8.5 years scanning the sky. One of its primary missions was to conduct an all-sky survey in X-rays, the first complete map of the X-ray universe. The survey found tens of thousands of sources: quasars, supernova remnants, binary star systems, and hundreds of galaxy clusters. Some of those clusters were already known from optical surveys. Others were new discoveries, hidden behind dust or simply too faint in visible light to have been noticed. And a significant number of them were sitting in or near the zone of avoidance. For the first time, astronomers had a tool that could see through the Milky Way's disk as if it were not there. Dust does not absorb X-rays the way it absorbs visible and infrared light. X-rays pass through almost unimpeded. The stars cluttering up the foreground do not matter. Stars emit X-rays, sure, but the emission from a typical star is faint compared to the glow from a cluster filled with tens of millions of degrees gas. Point an X-ray telescope at the zone of avoidance, and the foreground stars fade into the background. What stands out are the clusters. Rosat found several massive clusters in the region behind the Milky Way. The Norma cluster was among them, and it looked even more impressive in X-rays than it had in infrared. The hot gas filling the cluster emitted a bright, diffuse glow that extended across millions of light years. The gas was not distributed uniformly. It was clumpy, concentrated in the core where the galaxies were densest, thinning out toward the edges. You could see substructure in the emission, hints that smaller clusters or groups of galaxies had recently merged with the main body, their gas still not fully mixed into the larger reservoir. The X-ray data also gave astronomers something they could not get from optical or infrared observations: a direct measurement of the cluster's mass. The gas in a cluster is held in place by gravity. The hotter the gas, the faster its particles are moving, and the stronger the gravitational pull needs to be to keep it from flying apart. By measuring the temperature of the gas and the shape of its distribution, you can calculate how much mass is required to hold it in that configuration. Most of that mass is dark matter. The gas itself contributes some mass, and the galaxies contribute more. But the bulk of the gravitational pull comes from dark matter, which does not emit light at any wavelength, but reveals itself through its gravitational influence on everything around it. The mass estimates derived from Rosat's observations of the Norma cluster confirmed that it was enormous, on the order of 10 to the 15th solar masses, consistent with earlier estimates based on galaxy counts and velocity measurements. That made it one of the most massive clusters in the nearby universe. But the X-ray observations also revealed something else. The cluster was not sitting in isolation. The hot gas extended beyond the main body of the cluster, reaching out along filaments toward neighboring groups of galaxies. The cluster was connected. It was part of a larger network. Rosat's all-sky survey was a game changer, but it had limitations. The telescope's angular resolution was decent for an all-sky survey, but it was not sharp enough to pick out fine details in distant or heavily obscured regions. You could see that a cluster was there. You could measure its overall brightness and estimate its temperature. But if you wanted to study the internal structure, map the distribution of gas down to scales of individual galaxies, or trace the history of mergers and collisions within the clusters, you needed a more powerful instrument. That instrument was Chandra, the Chandra X Ray Observatoire, launched in July of 1999 aboard the Space Shuttle Columbia, and was deployed into a highly elliptical orbit that takes it more than a third of the way to the Moon at its farthest point. Chandra's mirrors are polished to a smoothness measured in atoms. Its angular resolution is sharp enough to distinguish features less than an arcsecond across, which at the distances of nearby galaxy clusters translates to spatial scales of a few tens of thousands of light years. That is the kind of resolution you need to see what is really happening inside a cluster. Chandra looked at the Norma cluster and saw details that Rosat had only hinted at. The gas was not just clumpy, it was turbulent. There were shock fronts, sharp boundaries where fast-moving gas had slammed into slower-moving gas and compressed it. There were cold fronts, regions where cooler, denser gas was sloshing around inside the cluster like liquid in a tank that had been shaken. The cluster was not a static object. It was dynamic, still settling from collisions that had happened millions or tens of millions of years ago. The shock fronts were particularly interesting because they told a story. When two galaxy clusters collide, they do not merge instantly. The process takes hundreds of millions of years. The galaxies pass through each other mostly unaffected. But the gas, which makes up the majority of the normal matter in a cluster, slams together. The collision heats the gas even further and sends shock waves propagating outward through the cluster like ripples on a pond. Those shock waves compress the gas, raising its temperature and density in a thin shell that moves outward at supersonic speeds. Chandra could see those shells. It could measure their temperature, their speed, their distance from the cluster center. From that information, you could reconstruct the collision history. How long ago did the clusters collide? How massive were they? How fast were they moving when they hit? The answers for the Norma cluster suggested that it had undergone at least one major merger in the past few 100 million years, possibly more. The cluster was still digesting its most recent meal. The turbulence in the gas, the misalignment between the distribution of galaxies and the distribution of hot gas, the presence of multiple temperature peaks in different parts of the cluster, all of it pointed to a violent and ongoing process of assembly. The Norma cluster was not a finished product, it was a work in progress. Around the same time Chandra was returning its first detailed images, Europe launched its own X-ray observatory, XMM Newton, named after Isaac Newton and short for X-ray Multi-Mirror Mission, went into orbit in December of 1999. Where Chandra prioritized angular resolution, XMM Newton prioritized sensitivity. Its mirrors were larger, its detectors more efficient at collecting photons. It could see fainter sources and measure weaker signals. The two observatories complemented each other. Chandra gave you the sharpest pictures. XMM Newton gave you the deepest exposures and the best spectroscopy. Spectroscopy is the process of splitting light into its component wavelengths and measuring how much energy is present at each wavelength. In X-ray astronomy, spectroscopy tells you the temperature of the gas, what elements it contains, and how fast it is moving. When gas in a galaxy cluster emits X-rays, the emission comes from specific atomic transitions. Iron atoms, oxygen atoms, silicon atoms, all of them stripped of most of their electrons by the intense heat, emit X-rays at specific energies when their remaining electrons jump between energy levels. By measuring the strength of those emission lines, you can figure out what the gas is made of. By measuring how much the lines are shifted in wavelength, you can figure out how fast the gas is moving toward or away from you. XMM Newton's spectrometers looked at the hot gas in the Norma cluster and confirmed what earlier surveys had suggested. The gas was enriched with heavy elements, iron, oxygen, silicon, magnesium, elements that are not produced in the Big Bang but are forged inside stars and then expelled into space when those stars die. The presence of heavy elements in the intra-cluster gas meant that stars in the cluster's galaxies had lived, burned through their fuel, exploded as supernovae, and dumped their enriched material into the surrounding medium. The gas had been processed. It was not primordial. It carried the chemical fingerprints of billions of years of stellar evolution. The temperature measurements from XMM Newton also confirmed that the gas was extraordinarily hot. Temperatures in the core of the cluster reached 50 to 70 million degrees Kelvin in some regions. That is several times hotter than the core of the Sun. Gas at that temperature does not cool quickly. It radiates energy, yes, but at those temperatures, the cooling time is measured in billions of years. The cluster could sit there glowing in X-rays for the rest of the age of the universe without losing a significant fraction of its thermal energy. The combination of Chandra's sharp images and XMM Newton's sensitive spectroscopy gave astronomers the most complete picture yet of the Norma cluster's structure and history. But the real revelation from X-ray astronomy was not about the Norma cluster itself. It was about what else was out there. Because as X-ray telescopes continued to map the zone of avoidance, they kept finding more clusters, not as massive as Norma in most cases, but substantial. Clusters weighing in at hundreds of trillions or a few quadrillion solar masses, sitting in adjacent patches of sky, connected by filaments of galaxies and gas, all of them contributing to the overall mass distribution in the Great Attractor region. One of the key projects aimed at mapping this hidden structure was called the Clusters in the Zone of Avoidance Survey, abbreviated CI. The survey combined X-ray data from ROSAT with optical and infrared observations to build a catalogue of clusters that had been missed by earlier surveys because of foreground obscuration. The results were striking. The survey identified dozens of clusters in regions that had previously appeared nearly empty in optical images. Some of them were relatively nearby, within a few 100 million light-years. Others were more distant, sitting at the far edge of the Great Attractor region or beyond. The distribution of these clusters was not random. They were arranged along filaments, the large-scale structures that connect clusters into the cosmic web. The Great Attractor region was not a single isolated overdensity. It was a node in the web, a place where multiple filaments converged, funneling galaxies inward from surrounding regions and building up a concentration of mass that extended across a volume hundreds of millions of light-years across. The X-ray observations also revealed that the Norma cluster, while the most massive single object in the region, was not responsible for all the gravitational pull. The mass was distributed. The clusters identified by CI and other surveys collectively contained enough mass to account for a significant fraction of the observed streaming motion. When you added up all the clusters, all the filaments, all the dark matter halos that surrounded them, the total mass in the Great Attractor region approached 10 to the 16th solar masses. That is 10 times the mass of the Norma cluster alone. 10 times. That number mattered because it explained why the Norma cluster by itself had never quite accounted for the full magnitude of the motion. The pull was coming from a distributed mass, not a single cluster, but a supercluster. A sprawling network of interconnected structures whose combined gravitational influence extended across hundreds of millions of light-years. The Norma cluster sat near the center of that network, the densest knot in the web. But it was not the engine. The engine was the entire region. The shift in understanding was profound. For more than a decade, astronomers had been searching for the Great Attractor, treating it as if it were a single object hidden somewhere behind the Milky Way, a monster cluster waiting to be discovered. The X-ray observations made it clear that there was no monster cluster. There was a monster region, a volume of space where an unusual amount of mass had accumulated over billions of years, pulling galaxies inward from all directions and shaping the motion of everything within a few 100 million light-years. This realization also explained why the streaming motion extended so far. A single cluster's gravitational influence falls off rapidly with distance. But a distributed mass, spread across hundreds of millions of light-years, can pull on distant galaxies with a cumulative effect that remains strong even at large separations. It is the difference between being pulled by a single magnet and being pulled by a field of magnets spread across a table. The total force can be larger and it can reach farther because you are adding up contributions from many sources instead of relying on one. The X-ray maps also showed something else that optical and infrared surveys had missed. The gas in the region was not confined to individual clusters. There were bridges, faint filaments of hot gas connecting one cluster to another, glowing at temperatures of a few million degrees. not as hot as the gas inside the clusters, but hot enough to emit detectable X-rays. These bridges were evidence of matter flowing along the cosmic web, funneling inward from surrounding voids and feeding the growth of the clusters. The Great Attractor region was not just a collection of clusters, it was an active construction site. Mass was still arriving. The structure was still being built. The detection of these intergalactic filaments was one of the most significant results to come out of X-ray astronomy in the 2000s. For decades, cosmologists had predicted that the cosmic web should be filled with warm, hot intergalactic medium, gas heated to temperatures between 100,000 and 10 million degrees by the gravitational collapse of structure. This gas was thought to contain a large fraction of the universe's normal matter, the so-called missing baryons that did not show up in galaxy surveys or in observations of cool hydrogen clouds. The problem was that gas at those temperatures is extremely difficult to detect. It does not emit much visible light. It does not emit radio waves efficiently. The only way to see it is in the ultraviolet or X-ray spectrum, and even then, the signal is faint. XMM Newton and Chandra found it. Not everywhere, but in a handful of carefully chosen lines of sight where the signal was strong enough to detect. The gas was there, glowing faintly between the clusters, tracing the filaments that theory said should exist. The discovery confirmed one of the key predictions of the standard model of cosmology and provided direct evidence that the cosmic web was not just a map of where galaxies are. It was a physical structure filled with gas and threaded through with dark matter, connecting the universe into a single coherent network. In the context of the Great Attractor, the detection of these filaments meant that the region was not pulling on isolated galaxies. It was pulling on the web itself. The filaments were funneling matter inward, delivering galaxies and gas to the clusters at the nodes where the filaments converged. The Great Attractor was not just a region of space, it was a convergence zone, a place where the cosmic web knotted itself into a tight cluster of interconnected structures. By the late 2000s, the picture that emerged from X-ray astronomy was radically different from what anyone had expected when the Great Attractor was first discovered in the 1980s. There was no single hidden cluster dominating the region. There was no monster pulling everything toward it. What existed instead was a complex, distributed overdensity made up of dozens of clusters, hundreds of groups, thousands of galaxies, and uncounted amounts of dark matter, all linked together by the gravity that shaped the cosmic web. The Norma cluster was the largest visible component, the landmark that had allowed astronomers to finally locate the region. But it was just one piece of a much larger structure. The mass was real, the pull was real. The streaming motion of galaxies toward the region was exactly what the velocity measurements had been showing for decades. The Great Attractor existed. But it was not the kind of thing you could point to on a map and say, there it is. It was diffuse, it was distributed. It was a gravitational basin stretching across 250 million light-years, filled with structure at every scale, pulling on the Milky Way and 100,000 other galaxies with a collective force that no single object could produce. X-ray astronomy had done more than just find the Great Attractor. It had redefined what the Great Attractor was, not an object, a region, not a destination, a flow pattern, not a mystery solved, but a mystery clarified. Because now that astronomers knew what they were looking at, now that they had mapped the distribution of mass with X-ray eyes that could see through the dust and stars cluttering up the foreground, they could ask the next question. How did this region fit into the larger structure of the universe? How far did its influence extend? And if the Milky Way was being pulled toward the Great Attractor, what was pulling the Great Attractor? The answer to that question would require stepping back, way back. looking not just at the Great Attractor region, but at the entire network of flows and structures across 1 billion light-years of space, mapping not just where galaxies are, but where they are going, building a picture not of one attractor, but of the whole cosmic web and our place within it. That is where the story goes next, to a structure so large that the Great Attractor, the thing that had haunted galaxy surveys for decades, turned out to be just one small part of it. The X-ray telescopes had done their job. They had found the Norma cluster. They had mapped the hot gas filling the space between galaxies. They had revealed structure where optical surveys had seen almost nothing, and in doing so, they had shifted the entire conversation. The Great Attractor was not a single monster cluster waiting to be discovered. It was something more diffuse, more distributed, a region filled with mass at every scale, pulling on everything nearby with a collective force that no single object could produce. But that realization, as useful as it was, left a more fundamental question unanswered. If the Great Attractor was not one thing, what exactly was it? How do you define a region that has no sharp boundaries, no single center, no clear beginning or end? And how do you measure the influence of something that is spread across hundreds of millions of light-years? The answer required rethinking what structure even means on the largest scales. Because the universe does not organize itself the way a city does, with a downtown core surrounded by suburbs fading into countryside. The universe organizes itself into a web, a network of filaments, sheets and nodes that stretches across billions of light-years in every direction. And the Great Attractor, it turned out, was not a destination. It was a knot in that web. A place where the filaments converged and the flow of matter became so strong that it dominated the motion of everything within a few 100 million light-years. To understand how astronomers came to that conclusion, you have to understand how the cosmic web works. And to understand the cosmic web, you have to go back to the beginning, not the beginning of this story, the beginning of everything. In the first fraction of a second after the Big Bang, the universe was almost perfectly smooth, almost. There were tiny fluctuations in the density of matter and energy, quantum ripples that got stretched to enormous scales by the rapid expansion of space during a period called inflation. Those ripples were small, differences in density of 1 part in 100,000, but they were enough. Because gravity amplifies differences. A region that starts out slightly denser than its surroundings pulls in more matter. As it pulls in more matter, it becomes even denser, and its gravitational pull grows stronger. The process feeds on itself. Over hundreds of millions of years, those tiny initial fluctuations grew into galaxies, clusters, and superclusters. But the growth was not uniform. The overdense regions did not collapse into spheres. They collapsed into sheets and filaments because the universe is three-dimensional and gravity works differently along different axes. Imagine a cloud of gas in space. If the cloud is perfectly spherical and perfectly uniform, gravity pulls equally from all directions and the cloud collapses into a ball. But if the cloud is slightly elongated, slightly flattened, gravity pulls harder along the short axis than along the long axis. The cloud collapses faster in one direction than in others. It turns into a pancake. Then the pancake develops ridges. The ridges become filaments. The filaments intersect at nodes where the density is highest. Those nodes become galaxy clusters. This process happened everywhere in the early universe. The result is a structure that looks, when you map it out, like a sponge, or a foam, or a web, which is the term that stuck. Filaments of galaxies stretching across tens or hundreds of millions of light-years, connecting clusters at the intersections. Between the filaments, vast empty regions called voids, where galaxies are rare, and the density of matter is far below the cosmic average. The web is not static. It is dynamic. Galaxies are moving along the filaments, flowing from the voids toward the densest nodes, pulled by gravity along the paths of least resistance. The Great Attractor is one of those nodes, a place where multiple filaments converge. Not the largest node in the universe, not by a long shot, but large enough to dominate the local flow, large enough to pull the Milky Way and tens of thousands of other galaxies into a coherent streaming motion toward a region roughly 200 million light-years away. The paradigm shift came in the 2000s when astronomers started mapping the cosmic web in detail. Earlier surveys had catalogued the positions of galaxies, building up three-dimensional maps of where things are. But position alone does not tell you much about structure. You can see clustering. You can see that galaxies tend to group together rather than spreading out uniformly. But you cannot see the web. You cannot see the filaments connecting one cluster to another. You cannot see the flows. For that, you need velocity information. You need to know not just where galaxies are, but where they are going. Velocity surveys are harder to do than position surveys because measuring a galaxy's velocity requires spectroscopy. You have to collect enough light from the galaxy to split it into a spectrum, identify absorption or emission lines, measure how much those lines have been shifted by the Doppler effect, and calculate the velocity from the shift. That takes time. You cannot just take a picture and move on. You have to sit on each galaxy long enough to get a clean spectrum. For a survey covering tens of thousands of galaxies, that means years of observing time. But by the early 2000s, the technology had improved to the point where large velocity surveys became feasible. Projects like the 2-degree field galaxy redshift survey, abbreviated 2DFGRS, and the Sloan Digital Sky Survey, known as SDSS, collected spectra for hundreds of thousands of galaxies across large fractions of the sky. The data allowed astronomers to build maps that showed not just where galaxies were located, but how they were moving. And when you plotted those motions, the cosmic web jumped out of the data. You could see galaxies streaming along filaments. You could see clusters sitting at the nodes where filaments intersected. You could see voids surrounded by sheets of galaxies, with the galaxies moving outward from the voids and inward toward the clusters. The Great Attractor fit perfectly into that picture. The region was not an isolated structure sitting in the middle of nowhere. It was a convergence zone, a place where several filaments met and fed matter into a dense cluster of superclusters. The Norma cluster was the largest single object at the center of that convergence, but it was surrounded by other clusters, smaller in most cases, but still massive. And beyond those clusters were filaments of galaxies, stretching outward for hundreds of millions of light years, connecting the Great Attractor region to the rest of the cosmic web. One of the most important adjacent structures is the Centaurus supercluster. It sits in roughly the same part of the sky as the Great Attractor, though slightly offset in direction and distance. The Centaurus supercluster is not a single cluster. It is a collection of clusters, groups, and smaller structures spread across a volume of space about 150 million light-years wide. The largest member of the Centaurus supercluster is the Centaurus cluster itself, a massive cluster containing hundreds of galaxies and weighing in at something like 10 to the 14th solar masses. Not as massive as the Norma cluster, but close. Then there is the Hydra cluster, sitting in a slightly different direction, but still within the broader Great Attractor region. The Hydra cluster is another massive structure, comparable in size to Centaurus. And beyond those, scattered across the surrounding area, are dozens of smaller clusters and groups, each one contributing to the total mass, each one pulling on nearby galaxies, each one adding to the collective gravitational influence of the region. When you add up all the mass in the Great Attractor area, all the clusters, all the groups, all the dark matter halos surrounding them, The total approaches 10 to the 16th solar masses. That is 100 times the mass of the Milky Way multiplied by 1,000,000. It is enough mass to bend the trajectories of galaxies across hundreds of millions of light years. And critically, the mass is not concentrated in one place, it is distributed, spread across a volume of space roughly 300 million light-years in diameter, depending on where you draw the boundaries. That distribution is what makes the Great Attractor so effective at pulling on distant galaxies. If all that mass were packed into a single cluster, the gravitational pull would be strong near the center and weak farther out. Gravity falls off as 1 over distance squared. Double the distance, and the force drops by a factor of 4. A single massive cluster can pull on nearby galaxies with considerable force, but by the time you reach distances of 100 million light-years or more, the pull becomes negligible. The Great Attractor does not work that way. The mass is distributed along filaments and concentrated at multiple nodes. When a galaxy far from the region feels the pull, it is not feeling the pull of one cluster, it is feeling the pull of dozens of clusters scattered across a huge volume, all tugging in roughly the same direction. The individual pulls add up. The result is a cumulative force that remains strong even at large separations. Think of it like this. If you are standing in a field and there is a single massive boulder 100 meters away, the boulder's gravity pulls on you. But the pull is so weak, you will never notice it. Now imagine the field is filled with boulders, hundreds of them, scattered across the landscape, all pulling in the same general direction. Each individual boulder contributes only a tiny force. But when you add up all the tiny forces, the cumulative effect becomes noticeable. That is what the Great Attractor is, a field of boulders, a distributed overdensity where the collective pull of many structures creates a flow strong enough to drag the Milky Way and tens of thousands of other galaxies toward it. The realization that the Great Attractor was a distributed structure rather than a single object came gradually. Early papers in the 1990s still referred to it as if it were a thing you could locate and point to. By the early 2000s, the language had shifted. Papers started describing the Great Attractor as a region, an overdensity, a convergence zone in the cosmic web. The shift was not just semantic, it reflected a deeper change in how astronomers understood large-scale structure. The universe does not have landmarks, it has flows. The motion of galaxies is not determined by individual objects. It is determined by the distribution of mass across enormous volumes. Mapping that distribution required combining data from multiple sources. Infrared surveys showed where the galaxies were. X-ray surveys showed where the hot gas was. Velocity surveys showed how the galaxies were moving. Gravitational lensing studies, which measure how much the light from distant galaxies is bent by foreground mass, provided independent estimates of where the dark matter was concentrated. Each technique had its strengths and weaknesses. Each one gave a partial picture. But when you combined them, the full structure started to emerge. One of the key insights from this work was that the Great Attractor region is not pulling everything toward itself. It is pulling some things toward itself, while other structures pull in other directions. The motion of any given galaxy is determined by the combined gravitational influence of everything nearby. The Great Attractor contributes to that motion. In many cases, it is the dominant contribution, but it is not the only contribution. There are other attractors, other nodes in the cosmic web where matter has concentrated and gravitational pulls compete. The most significant of those other attractors is the Shapley Supercluster. Shapley sits roughly 600 million light-years from the Milky Way, about 3 times farther than the Great Attractor. It is one of the most massive structures in the observable universe, containing more than 8,000 galaxies and weighing in at roughly 10 to the 16th solar masses. That makes it comparable in total mass to the entire Great Attractor region. And because it is so massive, it pulls hard. Even from 600 million light-years away, Shapley's gravitational influence is strong enough to affect the motion of galaxies in our neighborhood. For years, there was debate about how much of the Milky Way's motion was due to the Great Attractor and how much was due to Shapley. Some researchers argued that Shapley was the dominant influence and that the Great Attractor was just a waypoint, a concentration of mass that happened to lie along the line of sight between us and Shapley. Others argued that the Great Attractor was a significant attractor in its own right, and that Shapley's influence, while real, was secondary. The truth, as is often the case, turned out to be somewhere in between. Both structures contribute. The motion we observe is the result of both poles acting together. The way to disentangle the two contributions is to look at the velocity field in detail. If the motion were entirely due to the Great Attractor, you would expect galaxies to stream directly toward the Norma cluster from all directions. If the motion were entirely due to Shapley, you would expect galaxies to stream past the Great Attractor region toward Shapley. What astronomers actually see is a more complex pattern. Galaxies near the Great Attractor are streaming toward it. Galaxies farther out are streaming in a direction that points slightly beyond the Great Attractor, toward Shapley. The pattern suggests that both structures are pulling, and the relative strength of their pulls depends on where you are. This is one of the key features of the cosmic web. Motion is not determined by a single attractor, it is determined by the entire network. Galaxies flow along filaments, pulled by the clusters at the nodes where filaments intersect. If you are close to one node, that node dominates your motion. If you are farther away, other nodes start to contribute. The result is a complex velocity field that cannot be explained by pointing at one object and saying, "That is the thing pulling us." You have to look at the whole web. The Great Attractor region in this picture is a node, a convergence zone where multiple filaments meet. The Norma cluster is the densest point at the center of that convergence. The Centaurus supercluster, the Hydra cluster, and the surrounding groups and smaller clusters are additional concentrations of mass along the filaments feeding into the node. Together, they create a gravitational basin that extends across roughly 250 million light-years. Galaxies within that basin are being pulled inward from all directions. The Milky Way is one of those galaxies. So is Andromeda. So is the Virgo cluster, which sits about 50 million light-years from us in a different direction. All of them are streaming toward the Great Attractor, though their paths are also influenced by other nearby structures. The scale of this basin is difficult to wrap your mind around. 250 million light-years is not a distance you can visualize. Light from the far side of the Great Attractor region left its source when the most complex organisms on Earth were single-celled algae drifting in ancient oceans. By the time that light reaches us, multicellular life has evolved. Animals have crawled onto land, dinosaurs have come and gone, mammals have taken over, and humans have built telescopes to catch the photons. That is the kind of timescale we are talking about. And across that entire span of space, gravity is pulling, shaping the motion of galaxies, funneling matter inward along filaments, building structure. The distributed nature of the Great Attractor also explains why it took so long to understand what it was. Early observations in the 1980s detected the streaming motion and inferred that there had to be a large mass concentration somewhere in that direction. But the tools available at the time could not resolve the structure in detail. Optical surveys were blocked by the zone of avoidance. Infrared surveys were just beginning. X-ray surveys were crude. The best astronomers could do was estimate the total mass required to explain the motion and assume it was concentrated in a single cluster. That assumption turned out to be wrong, but it was a reasonable guess given the data. As better instruments came online in the 90s and 2000s, the picture got more complicated. Infrared surveys found galaxies where optical surveys had seen nothing. X-ray surveys found clusters scattered across the region. Velocity surveys revealed that the streaming motion was not converging on a single point. It was converging on a region, a volume of space filled with structure at every scale. The Great Attractor was not hiding behind the Milky Way. It was spread out across 250 million light-years, and only part of it happened to lie in the zone of avoidance. That realization was both a relief and a frustration. A relief because it explained why no single cluster had ever accounted for the full magnitude of the pull. The pull was coming from many clusters acting together. A frustration because it meant the Great Attractor could not be pinned down. There was no there. No single object you could point to and say, that is it. The Great Attractor was a collective effect, a region of enhanced density where the cosmic web had knotted itself into a tight cluster of interconnected structures. Astronomers started referring to the Great Attractor as a gravitational anomaly. The term was more accurate than calling it a cluster, but it was also less satisfying. An anomaly sounds like a mistake, like something that should not be there, but the Great Attractor is not a mistake. It is a natural consequence of how structure forms in an expanding universe. The cosmic web is full of nodes and filaments. Some nodes are larger than others, some filaments are denser than others. The Great Attractor region is an unusually large node, sitting in an unusually dense part of the web, pulling on an unusually large number of galaxies. It is not unique. There are other nodes like it scattered across the universe, but it is one of the largest and most massive in our cosmic neighborhood. And because we happen to live within its gravitational basin, it dominates the motion of our local group of galaxies. The extent of that basin is still being mapped. Early estimates in the 90s suggested the Great Attractor's influence extended across 100 million light-years or so. By the 2000s, as better velocity data became available, that estimate had grown to 200 million light-years. More recent work suggests the basin might be even larger. The exact boundaries are hard to define because the influence of the Great Attractor fades gradually with distance. There is no sharp edge where the pull suddenly stops. It blends into the pulls from other structures. Shapley, for example, pulls in a slightly different direction. There are other clusters and superclusters scattered across the sky, each contributing to the overall velocity field. The motion of any given galaxy is the vector sum of all those pulls. But within a radius of roughly 100 to 150 million light-years from the Great Attractor region, the flow is coherent. Galaxies are streaming inward. The motion is strong enough that it overrides the Hubble flow, the baseline expansion of the universe. That is the signature of a powerful attractor. When gravity is strong enough to pull galaxies toward a region faster than the expansion of space is carrying them apart, you know you are looking at a significant concentration of mass. The Great Attractor, in its modern incarnation, is not the mystery it once was. Astronomers know where the mass is. They know how it is distributed. They know which clusters and superclusters contribute to the pull. They have mapped the filaments connecting the region to the rest of the cosmic web. They have measured the velocity field in exquisite detail. The mystery has been replaced by a more subtle question. How did this region come to have so much mass? Why did the cosmic web produce such a large node in this particular location? Is there something special about the initial conditions in this part of the universe, or is the Great Attractor just a statistical fluctuation, an unusually large knot that formed by chance? That question does not have a clean answer yet. The distribution of mass in the universe is random in the sense that it is determined by quantum fluctuations in the early universe that we have no way of predicting. But it is not random in the sense that some regions will always end up denser than others just by chance. The Great Attractor could be one of those regions, a place where the dice happen to roll high, or it could be part of a larger pattern that we do not yet understand. What is clear is that the Great Attractor is not alone. It sits inside a much larger structure, a supercluster that extends far beyond the boundaries of the Great Attractor region itself. That supercluster includes the Milky Way. It includes the Virgo cluster. It includes tens of thousands of other galaxies scattered across a volume of space so large that light takes more than 500 million years to cross it. The Great Attractor is the gravitational focal point of that supercluster, the place where the flow converges, but it is not the whole story. The supercluster has a name that redefines our place in the universe and puts the Great Attractor into its proper context. That name is Laniakea. And understanding what Laniakea is, understanding how it was discovered and what it means for our cosmic address, requires stepping back even farther, looking not just at the Great Attractor, but at the entire network of flows across a billion light-years of space, mapping not just one basin, but all the basins, building a picture of the cosmic web that shows where we fit into the largest structures the universe has to offer. That is where the story leads next. The Great Attractor had been the target, the mystery, the thing astronomers spent 2 decades trying to see through dust and stars and the cluttered plane of our own galaxy. But the more carefully they mapped the velocity field, the more galaxies they catalogued, the more obvious it became that the Great Attractor was not the whole story. It was not even most of the story. It was a chapter in a much larger book. A node in a network that extended so far beyond the Great Attractor region that calling it our local neighborhood started to feel like a joke. The Milky Way is not just falling toward the Great Attractor, it is riding a current. A vast streaming motion that carries tens of thousands of galaxies through space along paths shaped by gravity across hundreds of millions of light years. And that current has a source, not a single point, not one attractor, a basin. A gravitational watershed so large that everything within 500 million light-years is either flowing into it or being held in place by something even larger, pulling in a different direction. That basin has a name, Laniakea, and it is where we live. The discovery of Laniakea was not the result of a single observation or a single breakthrough. It was the product of decades of patient work by researchers who understood that mapping the universe requires more than just knowing where things are. You have to know where they are going. Position tells you structure. Velocity tells you flow. And flow, it turns out, is a more fundamental way to define what a supercluster actually is than anything based on position alone. For most of the 20th century, astronomers defined superclusters by looking at maps. You catalog galaxies, plot their positions in 3 dimensions, and look for regions where the density is higher than average. Draw a boundary around the overdense region and call it a supercluster. That method works. It gave us the Virgo supercluster, a sprawling collection of galaxy groups and clusters that includes the Milky Way, the local group, and the massive Virgo cluster sitting about 50 million light-years away. For decades, the Virgo supercluster was considered our cosmic home, the largest structure we belong to. Roughly 110 million light-years across, containing somewhere around 100 galaxy groups, a few tens of thousands of galaxies total. It was big, it felt big, and it made sense as a definition because you could see it on a map. The galaxies were there, the overdensity was real, the structure was obvious, but the Virgo supercluster had a problem. It was not gravitationally bound. The galaxies inside it were not all moving together as a coherent unit. Some were streaming toward the Virgo cluster, others were streaming away. Still others were moving in directions that had nothing to do with Virgo at all. The structure held together visually on a map, but dynamically it was a mess. If you waited long enough, billions of years, the Virgo supercluster would not hold its shape. The expansion of the universe would pull it apart. The galaxies would drift away from each other, carried by the Hubble flow, and the structure would dissolve. That bothered some astronomers, because if a supercluster is not gravitationally bound, if it is not a real structure in the sense that it will persist over cosmological timescales, then what is it? A historical accident? A temporary arrangement of galaxies that happens to look like a structure but is not actually held together by anything? The question was not just philosophical, it cut to the heart of how you define what counts as a meaningful object in cosmology. Galaxies are real, they are bound by gravity. Clusters are real. Superclusters, under the old definition, were more ambiguous. The solution came from thinking about superclusters in a completely different way, not as regions of space where galaxies happen to be clustered, but as regions of space where galaxies are flowing. Basins of attraction, watersheds. Think of the surface of the Earth. Rain falls, water flows downhill, it collects in streams, streams merge into rivers, rivers flow into the ocean. If you want to define a watershed, you do not do it by looking at where the water is sitting at any given moment. You do it by tracing the flow. Every drop of water in a watershed is flowing toward the same destination. The boundary of the watershed is the ridge where water on one side flows one way and water on the other side flows a different way. That boundary is real. It is determined by the shape of the landscape. It does not change just because the water moves. Galaxies behave the same way. They flow through space, pulled by gravity toward regions of higher density. If you map the flow, if you trace which direction each galaxy is moving, you can identify basins of attraction, regions where all the galaxies are flowing inward toward a common center. The boundary of the basin is where the flow diverges. Galaxies on one side of the boundary flow into one basin. Galaxies on the other side flow into a different basin. That boundary defines a supercluster far more meaningfully than any arbitrary line you draw around an overdense region on a map. The problem with applying that method is that it requires incredibly precise velocity measurements, not just redshifts, which tell you how fast a galaxy is receding due to the expansion of the universe, but peculiar velocities, the component of a galaxy's motion that is not caused by expansion. The drift, the pull from nearby mass, measuring peculiar velocities is hard because the signal you are looking for is small compared to the Hubble flow. A galaxy sitting 100 million light-years away might be receding from us at 7,000 kilometers per second due to the expansion of space. Its peculiar velocity, the part caused by gravity pulling it toward a nearby cluster, might be only a few hundred kilometers per second. You are trying to measure a small deviation on top of a large background signal. The uncertainties are huge. You need extremely precise distance measurements, extremely precise redshifts, and you need them for thousands of galaxies to build up a reliable map of the flow field. By the early 2000s, that kind of data was starting to become available. Large redshift surveys had catalogued hundreds of thousands of galaxies. Distance measurement techniques had improved. Projects like the Cosmic Flows Survey, led by astronomer Brent Tully at the University of Hawaii, focused specifically on measuring peculiar velocities for galaxies across the nearby universe. Tully had been working on this problem for decades. In the 1970s, he co-developed the Tully-Fisher relation, a method for measuring galaxy distances based on how fast they rotate. By the 2000s, He was using that method and others to build a three-dimensional map of galaxy motions across a volume of space stretching out to several 100 million light-years. The breakthrough came in 2014. Tully and his collaborators, including Helene Courtois from the University of Lyon, Yehuda Hoffman from the Hebrew University of Jerusalem, and Daniel Pomarid from the Institute of Research into the Fundamental Laws of the Universe in France, published a paper in the journal Nature that redrew the map of our local universe. They had compiled peculiar velocity measurements for more than 8,000 galaxies and used those measurements to trace the flow field. The technique they used was sophisticated. They modeled the density field of the universe based on where galaxies are located, then used that density field to calculate the gravitational forces acting on each galaxy, then checked whether the predicted motions matched the observed peculiar velocities. When the model matched the data, they knew they had accurately reconstructed the flow. What the flow showed was striking. The Milky Way, the local group, the Virgo cluster, and tens of thousands of other galaxies were all streaming inward toward a common gravitational center. Not the Great Attractor, though the Great Attractor was part of it. The basin was much larger. It extended across roughly 500 million light-years and contained an estimated 100,000 galaxies. Everything within that volume was flowing inward, pulled by the collective gravity of all the mass in the region. The boundary of the basin, the ridge where flows diverged toward other attractors, defined the edge of the structure. Tully and his team needed a name for it. The structure was enormous. It contained everything we had previously called the Virgo Supercluster and much more. It redefined our cosmic address. Tully chose a name rooted in the place where the discovery was made: Hawaii. The Hawaiian language has a word, Laniakea, which translates roughly to immense heaven or open skies. It fit. The structure was immense, and it was, in a very real sense, the sky we live under. Not the sky you see at night, but the larger sky. The flow of galaxies that surrounds us and carries us through the universe. Laniakea became our home supercluster, not Virgo. Virgo was just one piece of Laniakea, a smaller substructure sitting near the edge of the basin. The Milky Way is part of Laniakea. Andromeda is part of Laniakea. The Great Attractor is part of Laniakea. Shapley, the massive supercluster 600 million light-years away, is not part of Laniakea. It sits beyond the boundary, in a different basin, pulling galaxies in a different direction. The ridge between Laniakea and Shapley marks the edge of our local flow. On one side, galaxies stream toward the Great Attractor and the structures within Laniakea. On the other side, they stream toward Shapley. The scale of Laniakea is difficult to convey: 500 million light-years across, 100,000 galaxies, a total mass of roughly 100 quadrillion suns. That is 10 to the 17th solar masses. The Milky Way, for comparison, weighs about 600 billion solar masses. Laniakea contains enough mass to account for more than 150,000 Milky Way-sized galaxies, even though the actual number of large galaxies is smaller because much of the mass is dark matter and intergalactic gas. The structure is not a sphere. It is irregular, elongated, shaped by the filaments and voids that surround it. The longest axis stretches more than 500 million light-years. The shortest is closer to 400 million. And somewhere near the outer edge of that structure, moving through space at 600 kilometers per second, is us. The Milky Way is not at the center of Laniakea. It is not even close to the center. We sit on the outskirts, in a relatively quiet region where the density is lower than average and the flow is gentle compared to the chaos near the core. The local group, the small cluster of galaxies that includes the Milky Way, Andromeda, and about 50 smaller companions, is drifting inward along one of the filaments that feeds into Laniakea's gravitational basin. Our motion is not dramatic. We are not plunging toward the center at breakneck speed. We are coasting, riding the current, moving at a few hundred kilometers per second relative to the center of mass of the structure, which sounds fast until you remember that the structure itself is 500 million light-years across. At our current speed, it would take us tens of billions of years to reach the core. By that time, the universe will have expanded so much that the journey will be meaningless. The center of Laniakea, the deepest point in the gravitational basin, sits somewhere in the direction of the constellations Norma and Centaurus. That is not a coincidence. The Great Attractor region, the concentration of clusters and superclusters that astronomers spent decades trying to map through the zone of avoidance, is the gravitational heart of Laniakea. It is not a single object, it is a convergence zone. The place where the filaments feeding into the basin meet and the flow is strongest. The Norma cluster, the Centaurus supercluster, the Hydra cluster, all of them sit near the core of Laniakea. They are the densest concentrations of mass in the structure, the nodes where the web knots itself most tightly. The discovery of Laniakea changed how astronomers think about large-scale structure. The old definition of superclusters, based on overdensities in galaxy counts, was replaced by a definition based on flow. A supercluster is a basin of attraction, a region where galaxies are gravitationally bound not to each other individually, but to the collective mass of the structure. The boundary of a supercluster is the watershed divide, the place where flows diverge. That definition is cleaner, it is more physical, and it is more meaningful because it tells you something about dynamics, not just about where things happen to be at this particular moment in cosmic history. Laniakea is not unique. It is one of many superclusters scattered across the observable universe. The nearby universe, mapped out to distances of 1 billion light-years or more, is filled with basins of attraction. Some are larger than Laniakea, some are smaller. Each one is a node in the cosmic web, a place where the filaments converge and matter flows inward. The boundaries between these basins define the largest structures in the universe, walls of galaxies, hundreds of millions of light-years long, marking the ridges where flows from adjacent basins meet and diverge. Visualizing Laniakea is not easy. The human brain is not wired to comprehend scales like 500 million light-years. Even the diagrams published in the Nature paper, which show the flow field as streamlines tracing the motion of galaxies, are abstractions. You are looking at a map of something that spans a volume so large that light takes 500 million years to cross it. A volume that contains more galaxies than there are stars in the Milky Way. A volume where every point is separated from every other point by distances so vast that the light from one end of the structure left its source before complex life existed on Earth. But the maps tell a story. They show that the universe is not random, it is organized. Galaxies do not drift aimlessly through space. They flow. They are pulled by gravity along paths determined by the distribution of mass across enormous volumes. And those flows carve out structure, basins, filaments, voids, walls. The cosmic web is not just a metaphor. It is a description of how matter moves and organizes itself under the influence of gravity over billions of years. Laniakea is where we fit into that web. It is our basin, the structure we are flowing through. The gravitational landscape that shapes our motion and the motion of every galaxy within 500 million light-years. The Great Attractor, which dominated the conversation for so long, is just one feature within that landscape. An important feature, yes. The largest and densest concentration of mass in our basin, but not the whole basin. Laniakea contains the Great Attractor the way a watershed contains a valley. The valley is the lowest point, the place where the water collects, but the watershed is the entire region where water flows toward that valley. The Great Attractor is the valley, Laniakea is the watershed. The shift in perspective was profound. For decades, astronomers had been focused on finding the Great Attractor, treating it as the final answer to the question of why the Milky Way is moving. The discovery of Laniakea made it clear that the Great Attractor was not the final answer. It was one piece of a much larger puzzle. The motion of the Milky Way is determined by the flow field within Laniakea, which is itself determined by the distribution of mass across the entire basin. The Great Attractor contributes to that flow. It is the dominant feature near the center of the basin, but it is not the engine. The engine is the entire structure. Every cluster, every filament, every concentration of dark matter spread across 500 million light-years, all of it pulling together, shaping the motion of galaxies, carving out the flow that carries us through space. One of the most striking aspects of the Laniakea discovery is how much of the structure was already known but not recognized for what it was. The Virgo supercluster had been mapped for decades. The Great Attractor had been studied intensively since the 1980s. Shapley had been catalogued in the 1930s. All the pieces were there. What was missing was the framework that tied them together. The flow-based definition of a supercluster provided that framework. It showed that Virgo was not a separate structure. It was part of a larger basin. The Great Attractor was not an isolated anomaly. It was the core of that basin. Shapley was not just a distant cluster. It was a separate attractor, sitting in a different basin, pulling in a different direction. The boundary between Laniakea and the Shapley Basin is one of the most interesting features in the local universe. It is not a wall. It is not a physical barrier. It is a surface in space where the gravitational pull from Laniakea and the pull from Shapley are balanced. Galaxies sitting exactly on that surface are not flowing toward either attractor. They are caught between two pulls, drifting slowly or sitting nearly stationary relative to the overall flow. Galaxies just inside the boundary flow toward Laniakea. Galaxies just outside flow toward Shapley. The boundary is dynamic. It shifts as mass moves and as the structure evolves. But on timescales of billions of years, it is stable. It marks the true edge of our local supercluster. The size of Laniakea also puts the Great Attractor mystery into a new light. The streaming motion that astronomers detected in the 1980s, the motion that led to the search for the Great Attractor in the first place, was not just the Milky Way falling toward a single cluster. It was the Milky Way flowing through Laniakea. The motion is coherent across the entire basin because every galaxy in the basin is responding to the same gravitational landscape. The Great Attractor sits near the bottom of the basin, so galaxies near the Milky Way are streaming in that direction. But galaxies on the other side of the basin, farther from the Great Attractor and closer to Shapley, are streaming in a slightly different direction. The flow is not radial. It is more complex, shaped by the distribution of mass across the entire structure. Mapping Laniakea also revealed how interconnected the cosmic web really is. Laniakea is not isolated. It is connected to neighboring basins by filaments of galaxies that stretch across the voids. Some of those filaments carry galaxies inward, feeding the basin. Others carry galaxies outward, pulled away by the attraction of neighboring structures. The balance between inflow and outflow determines whether the basin grows over time or remains stable. In the case of Laniakea, the inflow is stronger. The basin is still growing. It is pulling in matter from surrounding voids, accreting galaxies and gas, building up its mass. Billions of years from now, if the expansion of the universe does not tear it apart first, Laniakea could be significantly more massive than it is today. The Hawaiian name turned out to be more appropriate than the team realized when they chose it. Laniakea means immense heaven. But it also carries connotations of openness, of vast spaces, of a sky that stretches farther than you can see, that captures the essence of what the structure represents. It is not a confined region, it is not a box, it is a flow, a basin that encompasses everything we can see in our local neighborhood and extends far beyond. It is the largest structure we know we are part of, our cosmic address. The answer to the question, where do we live, if you zoom out far enough that individual galaxies stop mattering. Before Laniakea, the answer to that question was vague. We live in the local group. We live in the Virgo supercluster. We live in the universe. Those answers were all true, but they did not convey the full picture. The local group is too small. It is a single galaxy cluster, a tiny piece of the larger structure. The Virgo supercluster was too arbitrary. It was defined by density, not by dynamics, and it turned out to be just a part of something bigger. The universe is too large. It is everything. Saying we live in the universe is like saying you live on Earth. True, but not useful. Laniakea is the right scale. It is the structure that actually defines our place in the cosmic web. It is the basin we are flowing through, the region where gravity pulls everything inward toward a common center. It is large enough to encompass all the major structures in our neighborhood, the local group, Virgo, the Great Attractor, but small enough to be mappable, to be something you can study and understand as a single coherent object. Laniakea is where we live. But even Laniakea is not the end of the story, because the flow does not stop at the boundary. Laniakea itself is moving. The entire basin, all 500 million light-years of it, is drifting through space, not because it is being pulled by something inside the basin, because it is being pulled by something outside. Shapley is one of those external attractors, and there are others, larger structures farther away, pulling in different directions, shaping the motion of Laniakea the way Laniakea shapes the motion of the Milky Way. There is also something else, something astronomers did not expect, a region of space on the opposite side of the sky from Shapley, a region that is not pulling, it is pushing, or rather, it is underdense, a vast void, hundreds of millions of light-years across, where the density of galaxies is far below the cosmic average, and that underdensity has an effect. It repels, not through some exotic force, through the absence of gravity. When one side of a basin has more mass than the other side, the basin drifts toward the mass, but it is also drifting away from the low-density region. The push from the void and the pull from the distant attractor combine to produce a motion that cannot be explained by looking at local structures alone. That void has a name, the dipole repeller, and it is the next piece of the puzzle. Because if Laniakea redefined our cosmic address, the dipole repeller redefined how we think about cosmic motion. It showed that the universe does not just pull, it also pushes, and the Milky Way, moving at 600 kilometers per second through space, is being shaped by both. Laniakea was supposed to be the answer, the structure that finally made sense of our motion, the basin that contained the Milky Way, the Great Attractor, and everything flowing between them. 500 million light-years across, 100,000 galaxies. The largest coherent structure we knew we belonged to. It redefined our cosmic address. It turned the Great Attractor from a mystery into a landmark. It gave us a framework for understanding why galaxies move the way they do. And for a brief moment, it felt like the story was complete. It was not. Because once you map a basin of attraction, once you trace the flows and define the boundaries, the next question arrives immediately. What is the basin doing? Laniakea is not sitting still. The entire structure, all 500 million light-years of it, is moving through space. At about 600 kilometers per second, the same speed the Milky Way is moving. That is not a coincidence. The Milky Way is moving at 600 kilometers per second because it is being carried along by Laniakea. But Laniakea itself is drifting. And if Laniakea is drifting, something outside the basin must be pulling it, or pushing it, or both. The answer turned out to be both. The first hint came from the Shapley Supercluster. Shapley sits roughly 600 million light-years from the Milky Way, about 3 times farther than the center of the Great Attractor region. It is one of the most massive structures in the observable universe. More than 8,000 galaxies packed into a volume of space spanning a few hundred million light-years. Total mass somewhere around 10 to the 16th solar masses. That makes it comparable in mass to Laniakea itself, possibly larger depending on how you draw the boundaries, and it is pulling hard. For years, astronomers had debated how much of the Milky Way's motion was due to the Great Attractor and how much was due to Shapley. The velocity measurements showed that our motion was not aimed directly at the center of the Great Attractor. It was aimed slightly past it, in a direction that pointed more or less toward Shapley. That suggested Shapley was contributing to the pull, but the distance made the math uncomfortable. Gravity falls off with distance. Shapley is 3 times farther than the Great Attractor. Its pull on us should be 9 times weaker. Even accounting for its larger mass, it should not dominate our motion. The Great Attractor, being closer, should be the primary influence, unless the Great Attractor and Shapley were both pulling. Unless our motion was the result of a combined gravitational field shaped by multiple attractors at different distances, each contributing to the overall flow. That idea had been proposed before, but proving it required mapping the velocity field across enormous volumes of space. Not just within Laniakea, but beyond it, out to distances where Shapley and other massive structures were located. That kind of mapping was not possible in the 1990s. By the 2010s, it was starting to become feasible. The breakthrough came from the same team that had discovered Laniakea: Brent Tully, Hélène Courtois, Yehuda Hoffman, Daniel Pomered. They had spent years compiling peculiar velocity measurements for tens of thousands of galaxies, tracing the flow field, defining basins of attraction. Once Laniakea was mapped, they kept going. They extended the survey farther out, they added more galaxies, they refined the models, and they started asking what was happening on the other side of the sky, on the opposite side from Shapley. What they found was nothing, literally, a vast region of space where the density of galaxies was far below the cosmic average, a void. Voids are not unusual in the universe. The cosmic web is full of them. They are the empty spaces between the filaments and clusters, regions where matter has been pulled away by the gravity of surrounding structures, leaving behind volumes of space that are almost empty. Most voids are a few tens of millions of light-years across. Some are larger, a few reach 100 million light-years. The void on the opposite side of the sky from Shapley was bigger than that, much bigger. They called it the dipole repeller. The name was chosen carefully. A dipole is a pair of opposite poles. In this case, the 2 poles were Shapley, a massive overdensity pulling on Laniakea from one direction, and the void, a massive underdensity pushing from the opposite direction. The term repeller was more provocative. Voids do not repel in the sense of exerting a force that pushes things away. Gravity does not work that way. There is no anti-gravity, no repulsive force. A void is just a region with less mass than average, but less mass means less gravitational pull, and when one side of a structure has less pull than the other side, the structure drifts toward the side with more pull. From the perspective of an observer inside the structure, it feels like the void is pushing. The low-density region on one side and the high-density region on the other combine to produce a motion that cannot be explained by looking at either one alone. The dipole repeller is enormous. Estimates put its size at several hundred million light-years across. It is not completely empty. There are galaxies in it, scattered thinly across the void, but the density is low, significantly lower than the cosmic average. Low enough that the region exerts far less gravitational pull than the space around it. And because gravity pulls everything toward mass, galaxies on the edge of the void are pulled away from it, toward the denser regions surrounding it. Laniakea sits on the edge of that void. On one side, Shapley and other massive structures pull inward. On the other side, the void offers almost no resistance. The result is that Laniakea drifts away from the void and toward Shapley. The discovery was published in 2017 in the journal Nature Astronomy. The paper, led by Yehuda Hoffman, presented a model of the large-scale velocity field that included both attractors and repellers. The model showed that the motion of Laniakea, and by extension the motion of the Milky Way, could not be explained by Shapley alone. You needed the void. The push from the low-density region on one side was just as important as the pull from the high-density region on the other. Together, they shaped the flow. The implications were profound. For decades, cosmologists had focused almost entirely on overdensities, clusters, superclusters, filaments, the places where mass collected and gravity was strong. Voids were treated as background, empty spaces that did not do much. The dipole repeller showed that voids are active participants in shaping cosmic flows. They do not just sit there. They influence motion by their absence. By having less mass than the surrounding regions, they create gradients in the gravitational field, and those gradients drive flows just as effectively as the pull from a massive cluster. Think of it this way. Imagine you are standing on a hill. If there is a valley below you, you will roll downhill toward the valley. But you are not just rolling because the valley is pulling you. You are rolling because the hill is higher than the valley. The difference in elevation is what matters. Now imagine the valley is not a single low point, but an entire flat plain stretching off into the distance. You are still on a hill. You will still roll downhill. But the direction you roll depends on where the plane is relative to the peaks around you. If there are mountains on one side and a plain on the other, you roll toward the plain, not because the plain is pulling you, but because the mountains are pushing you away by comparison. The plain is a repeller. The dipole repeller works the same way. It is not exerting a force, it is shaping the landscape. The gravitational field across the region surrounding Laniakea is not uniform. On one side, toward Shapley, the field is steep, lots of mass, strong pull. On the other side, toward the void, the field is flat, little mass, weak pull. Laniakea sits between the two and drifts toward the steep side. The motion is determined by the difference, not by the absolute strength of the pull from Shapley alone. That realization changed how astronomers thought about large-scale flows. The motion of galaxies across the universe is not just about where the mass is, it is about where the mass is not. Voids matter. They shape the velocity field just as much as clusters do. And if you want to understand why a galaxy or a supercluster is moving in a particular direction, you cannot just look at the attractors. You have to look at the repellers too. The dipole repeller also explains something that had been bothering researchers for years: the direction of the Milky Way's motion. When you measure our velocity relative to the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang, you find that the Milky Way is moving at about 600 kilometers per second toward the constellation Centaurus. That direction points roughly toward the Great Attractor, but not exactly. The motion is offset slightly. If you draw a line from the Milky Way toward the center of the Great Attractor region, and then draw a line showing our actual motion, the two lines do not align perfectly. The offset is small, only a few degrees, but it is real, and for years no one had a good explanation for it. The dipole repeller model explained the offset. The motion is not aimed at the Great Attractor. It is aimed at the combined gravitational center of the entire flow field, which includes not just the Great Attractor, but Shapley, the void, and every other overdensity and underdensity across hundreds of millions of light years. When you add up all those contributions, the net direction of the flow is slightly offset from the Great Attractor. The offset is exactly what the model predicts. The match between the prediction and the observation was so close that it left little room for doubt. The dipole repeller was real. The discovery also raised a more uncomfortable question. If Laniakea's motion is being shaped by structures hundreds of millions of light years away, what is shaping the motion of those structures? Is Shapley being pulled by something even farther out? Is the dipole repeller itself part of a larger pattern of voids and filaments that extends across billions of light years? Where does it stop? The answer is that it does not stop. Not at any scale we have been able to map. The cosmic web extends as far as we can see. Filaments connect to filaments. Clusters connect to superclusters. Superclusters connect to even larger structures that do not have names yet because we are only beginning to map them. The flows we observe in our local neighborhood, the motion of the Milky Way toward the Great Attractor, the drift of Laniakea toward Shapley, are all part of a much larger pattern, a hierarchy of flows nested inside each other like Russian dolls, each one shaped by the distribution of mass and voids at progressively larger scales. Mapping that hierarchy is one of the grand challenges of modern cosmology. It requires velocity measurements for galaxies across billions of light years, not just a few thousand galaxies, millions. Each one carefully measured to determine not just where it is, but where it is going. The task is monumental, and it is ongoing. Surveys like Cosmic Flows, which Tully and his collaborators continue to run, are adding new galaxies every year. Other projects, like the Sloan Digital Sky Survey and its successors, are compiling redshifts for hundreds of thousands of objects. The data is accumulating, the maps are getting better, but the universe is large. Mapping the entire velocity field out to distances of billions of light years will take decades. Even with incomplete data, the picture that is emerging is striking. The universe on the largest scales is not random, it is organized. Flows are coherent across enormous volumes. Galaxies do not just wander, they stream. They follow paths determined by the gravitational landscape shaped by billions of years of structure formation. And that landscape has features at every scale: local flows within galaxy groups, flows within clusters, flows within superclusters, flows between superclusters, each one nested inside the next, each one contributing to the overall motion of everything within it. The Milky Way's motion in this picture is not unique. It is typical. Every galaxy in the universe is moving under the influence of the structures around it. Some galaxies are flowing toward nearby clusters. Others are flowing along filaments. Still others are drifting through voids, pulled gently by the distant attractors at the edges. The specific numbers vary. The distances vary. The speeds vary. But the underlying process is the same everywhere. Gravity pulls, voids repel, flows emerge, structure forms. The discovery of the dipole repeller also had implications for cosmological models. The standard model of cosmology, the framework that describes how the universe evolved from the Big Bang to the present, predicts that structure should form hierarchically. Small overdensities grow into larger ones. Clusters merge into superclusters. Superclusters link into filaments. The process is driven by gravity acting on the initial density fluctuations left over from the early universe. Those fluctuations were imprinted during inflation, stretched to enormous scales, and then grew over billions of years as gravity amplified the differences. The model makes specific predictions about what the large-scale structure should look like, how many voids there should be, how large they should be, how they should be distributed relative to the filaments and clusters. The dipole repeller fits those predictions. Its size, its location, its effect on the surrounding velocity field, all of it matches what the standard model says should exist. That is reassuring. It means the model is working, but it also means that voids are not anomalies. They are expected features of the cosmic web. Every simulation of structure formation produces voids. The dipole repeller is just one example of a generic phenomenon that should be common throughout the universe. That raises an interesting question. If voids are common, and if they shape flows the way the dipole repeller shapes Laniakea's motion, then every supercluster in the universe should be influenced by both attractors and repellers. Every large-scale flow should be a dipole flow, shaped by the push from a void on one side and the pull from a cluster on the other. The implication is that the universe is full of these dipoles, pairs of attractors and repellers working together to drive flows across billions of light years. Mapping them all would give us a complete picture of how mass and motion are connected on the largest scales. That picture is starting to come into focus. Recent work has identified several other large-scale flows similar to the one Laniakea is riding. There is a flow toward a structure called the Shapley concentration, which is not just the Shapley supercluster itself, but a broader region of enhanced density that includes several other massive clusters. There is a flow away from a void in the direction of the constellation Eridanus, on the opposite side of the sky from Shapley. There are flows connecting the local universe to even more distant structures that we are only beginning to catalogue. Each flow is shaped by a combination of attractors and repellers. Each one tells a story about how mass is distributed across that region of space. The scale of these flows is staggering. The Laniakea flow extends across 500 million light-years. The flow toward Shapley extends even farther, encompassing structures out to distances of 1 billion light-years or more. The flows do not have sharp boundaries. They blend into each other. A galaxy sitting at the edge of one flow might also feel the pull from an adjacent flow. The velocity field is continuous, smooth at large scales, turbulent at smaller scales, but always connected. There are no isolated regions, no walls that stop the influence of gravity from propagating outward. Every part of the universe pulls on every other part, and the strength of the pull decreases with distance but never drops to zero. This interconnectedness is one of the most beautiful aspects of large-scale structure. The universe is not a collection of separate objects sitting in otherwise empty space. It is a network, a web of gravitational interactions where every galaxy, every cluster, every void contributes to the overall pattern. You cannot understand the motion of the Milky Way without understanding Laniakea. You cannot understand Laniakea without understanding the dipole repeller and Shapley. And you cannot understand those structures without looking even farther out to the flows and structures that surround them. The universe is a system, and like any system, you have to look at the whole thing to understand how the parts work. The dipole repeller discovery also highlighted a practical challenge. Measuring the velocity field requires precise distance measurements. Redshift tells you how fast a galaxy is receding due to the expansion of the universe, but it does not tell you how far away the galaxy is unless you know its peculiar velocity. Peculiar velocity requires an independent distance measurement, and distance measurements are hard. The farther away a galaxy is, the harder it gets. The uncertainties grow, the methods become less reliable. By the time you reach distances of several 100 million light-years, the error bars on your distance estimates can be tens of millions of light-years or more. That uncertainty translates directly into uncertainty in the velocity field. The result is that the maps of large-scale flows are fuzzy. They show the general pattern, the broad features, the locations of major attractors and repellers, but the details are uncertain. Exactly how massive is the dipole repeller? Exactly how strong is its influence on Laniekea's motion? Those questions do not have precise answers yet. The models make predictions. The observations are consistent with those predictions. But the error bars are large enough that there is still room for debate. Improving the measurements requires better distance indicators, new methods that work at larger distances with smaller uncertainties. Projects like the James Webb Space Telescope are helping. Webb can observe galaxies at enormous distances with unprecedented precision. Its infrared capabilities allow it to see through dust and detect faint sources that Hubble would have missed. Over time, as Webb and other next-generation telescopes collect more data, the maps will improve, the flows will become sharper, the uncertainties will shrink. But the task is slow. Astronomy is a patient science. The dipole repeller also forced a reckoning with how we talk about structure. For decades, astronomers had used the word attractor to describe concentrations of mass that pull on surrounding galaxies. The Great Attractor was the most famous example. Shapley was another. The language implied that these structures were the primary drivers of motion, the things that mattered. Voids were background, passive, uninteresting. The dipole repeller flipped that narrative. It showed that voids are not passive, they are active participants. They shape flows just as much as attractors do. The language needed to change. Flows are not driven by attractors alone, they are driven by gradients in the gravitational field, and those gradients are shaped by both overdensities and underdensities. The shift in language reflected a deeper shift in understanding. The universe is not made of things, it is made of fields, gravitational fields, matter fields, energy fields. The distribution of those fields determines how everything moves. Galaxies are not objects being pulled by other objects. They are test particles moving through a gravitational landscape. The landscape has peaks and valleys. The peaks are clusters and superclusters. The valleys are voids. Galaxies flow downhill from the valleys toward the peaks, following the contours of the landscape. The dipole repeller is one of the valleys. Shapley is one of the peaks. Laniakea sits on the slope between them, sliding downhill. That picture is elegant. It unifies attractors and repellers into a single framework. It explains flows without requiring any exotic physics. Gravity is enough. Ordinary gravity, acting on ordinary matter, distributed across the universe according to the density fluctuations left over from the Big Bang. The flows we observe today are the direct consequence of those initial fluctuations amplified by billions of years of gravitational collapse. The dipole repeller is not a mystery, it is a prediction, a feature that had to exist if the standard model was correct. Finding it was confirmation that the model works, but the model also has limits. It predicts the existence of voids and flows. It does not predict their exact locations or sizes. Those are determined by the specific pattern of density fluctuations in the early universe, which are effectively random. Different regions of the universe have different patterns, different voids, different flows. The dipole repeller is unique, not because voids are rare, but because it happens to be the void sitting next to us. If we lived in a different part of the universe, we would see a different void. We would measure a different flow. But the underlying physics would be the same. That universality is one of the strengths of the standard model. It does not require fine-tuning. It does not require special conditions. It just requires gravity and time. Give the universe 14 billion years to evolve, and structures like the dipole repeller and Laniakea will form naturally. The details vary, but the process is generic. The cosmic web is not an accident. It is the inevitable outcome of structure formation in an expanding universe. The discovery of the dipole repeller also opened a new line of research. If voids shape flows and flows shape structure, then studying voids might tell us as much about the universe as studying clusters. Voids are harder to observe because they contain fewer galaxies, but they are larger. They occupy more volume. In fact, most of the universe by volume is void. The filaments and clusters are the exception, not the rule. If you picked a random point in space, it would most likely be inside a void. Understanding voids is understanding the majority of the universe. Recent studies have started cataloging voids in detail, measuring their sizes, their shapes, their density profiles. Some voids are nearly spherical, others are elongated, stretched along the filaments that surround them. Some are completely empty, containing almost no galaxies at all. Others have a few scattered galaxies drifting through them, like ships in the open ocean. Each void is different, but they all follow the same basic rules: low density, weak gravitational pull, gradual expansion as the surrounding filaments pull matter away. Voids grow over time. They start small, just slightly underdense regions in the early universe. As structure forms around them, galaxies flow outward and the voids expand. Billions of years from now, the dipole repeller will be even larger than it is today, emptier, more diffuse. The filaments surrounding it will have pulled even more matter away, leaving behind a region that is closer to true emptiness. But voids never become completely empty. There is always some residual matter, a few galaxies left behind, gas and dust too diffuse to form stars. Dark matter, which does not clump as tightly as normal matter and fills even the voids with a faint background density. Voids are not voids in the absolute sense. They are underdensities, regions where the density is far below average but not zero. The distinction matters because it means voids still have gravity, weak gravity, but not none, and that weak gravity still affects the motion of anything passing through or near the void. The interplay between attractors and repellers is what gives the cosmic web its structure. Without voids, the universe would collapse into a single giant cluster. Every galaxy would fall toward every other galaxy, and eventually everything would merge into one enormous structure. But voids prevent that. They create boundaries, regions where the pull from distant attractors is too weak to overcome the local expansion of space. Galaxies inside voids drift apart. Galaxies outside voids fall inward toward the filaments. The result is a network, a web. A balance between collapse and expansion that produces structure at every scale. That balance is delicate. It depends on the density of matter in the universe, the rate of expansion, the strength of gravity. Change any of those parameters and the structure changes. In a universe with more matter, voids would be smaller, the filaments would be denser, the clusters would be larger. In a universe with less matter, voids would dominate, the web would be sparser, clusters would be rare. The universe we observe sits somewhere in the middle. Enough matter to form rich structure, not so much that everything collapses. The balance is what makes the cosmic web possible. The dipole repeller, Shapley and Laniakea are all part of that balance. They are features in a landscape shaped by 14 billion years of gravitational evolution. They are not permanent, they are dynamic, they are still forming, still growing, still pulling and pushing on each other. Billions of years from now, the map will look different. Some clusters will have merged, some voids will have expanded, some filaments will have thickened. The flows will change direction as the mass distribution shifts. but the process will be the same. Gravity acting on matter, shaping structure, driving motion. And somewhere in all of that, on the slope between a void and a supercluster, riding a flow shaped by structures hundreds of millions of light years away, is us, the Milky Way. A single galaxy in a universe of trillions, moving at 600 kilometers per second toward a destination we will never reach. The Great Attractor, Laniakea, the dipole repeller, all of them are part of the machinery that drives that motion. They are the unseen architects of our trajectory through space, the forces that shape not just where we are, but where we are going. And understanding them means understanding the universe itself, not as a static collection of objects, but as a dynamic system. A web of flows and fields and forces that connects everything to everything else across distances so vast that the light crossing them carries the history of the universe in every photon. That is the story the dipole repeller tells. That is what lies beyond Laniakea, not an endpoint. A continuation, a reminder that no matter how far out you zoom, there is always something larger pulling the strings. So here we are, 8 chapters in. 8 chapters spent tracing the motion of galaxies, peering through dust clouds, mapping X-ray emissions, defining basins of attraction, discovering voids that push as much as clusters pull. 8 chapters following a thread that started with a simple observation in the 1980s. The Milky Way is moving, and something out there, something enormous, is pulling it. We found the thing, or rather, we found where the thing is supposed to be, the Great Attractor, the Norma cluster, the sprawling network of superclusters and filaments filling the zone of avoidance. Laniakea, the 500 million light-year basin that defines our place in the cosmic web. The dipole repeller, the void on the opposite side of the sky, pushing us away as Shapley pulls us forward. All of it mapped, all of it measured, all of it explained, to the extent that anything in cosmology is ever fully explained. But knowing where something is and knowing what it is are not the same thing. We know the Great Attractor region contains tens of thousands of galaxies. We know it sits at the center of Laniakea's gravitational basin. We know it has a mass of roughly 10 to the 16th solar masses, give or take. We can point a telescope at it, or at least toward it, and catalog the clusters scattered across that part of the sky. We can measure the velocity of every galaxy within a few hundred million light years and trace how they flow toward the region. We can build models that predict the motion and check those predictions against the data. The match is good. The mystery, in the narrow sense, has been solved, except it has not. Because the deeper you look at the Great Attractor, the more obvious it becomes that the real mystery is not the Great Attractor itself. The real mystery is what the Great Attractor is made of, and most of it is invisible. The visible galaxies, the stars and gas and dust that we can observe with telescopes, account for only a fraction of the mass. The Norma cluster contains thousands of galaxies. Each one is a collection of hundreds of billions of stars. Add them all up, and the total mass is staggering. But it is not enough, not nearly enough to explain the gravitational pull, the motion of galaxies across the Great Attractor region, the streaming velocities, the coherence of the flow across hundreds of millions of light years. All of it requires far more mass than the visible matter can provide. The shortfall is not small. It is not a rounding error. The visible matter accounts for maybe 15 or 20% of the total mass. The rest is something else, something that does not emit light, something that does not absorb light, something that does not interact with electromagnetic radiation at all. We call it dark matter, and it is the scaffolding that holds the Great Attractor together. Dark matter is not a new idea. Astronomers have known about it since the 1930s, when Fritz Zwicky measured the velocities of galaxies in the Coma cluster and realized they were moving too fast to be held together by the gravity of the visible stars alone. Either the cluster contained a huge amount of unseen mass, or the galaxies should have flown apart long ago. The cluster had not flown apart, therefore unseen mass. Zwicky called it dark matter, and the name stuck. For decades, the idea was controversial. Some astronomers accepted it. Others argued that the observations could be explained by modifying the laws of gravity instead of invoking invisible matter. The debate dragged on through the 70s and 80s, with evidence piling up on both sides but no clear resolution. By the 90s, the evidence had become overwhelming. Galaxy rotation curves showed that stars in spiral galaxies were orbiting too fast to be explained by the gravity of the visible disk. Gravitational lensing studies showed that clusters bent the light from background galaxies far more than the visible mass could account for. Simulations of structure formation in the early universe showed that you could not reproduce the observed distribution of galaxies without including a large component of dark matter to seed the initial collapse. The case was closed. Dark matter was real, whatever it was. And that is the frustrating part. We know dark matter exists. We can measure its gravitational effects. We can map its distribution using lensing and galaxy velocities. We can simulate how it clumps and forms halos and pulls ordinary matter into the structures we see today. But we do not know what it is. We do not know what particles it is made of, or whether it is made of particles at all. We do not know why it does not interact with light. We do not know how to detect it directly. For nearly a century, we have been studying an invisible substance that outweighs everything we can see by a factor of 5 to 1, and we still have no idea what it is. The Great Attractor is a reminder of how completely dark matter dominates the universe. The visible galaxies, the stars that light up the night sky, the nebulae and quasars and black holes, all of it is just decoration. The real structure, the gravitational framework that shapes the cosmic web, is built out of dark matter. The filaments connecting galaxy clusters are dark matter filaments. The halos surrounding galaxies are dark matter halos. The basins of attraction that define superclusters like Laniakea are carved out by the gravity of dark matter distributed across hundreds of millions of light years. Ordinary matter, the stuff we are made of, the stuff we can see and touch and measure directly, is a passenger. It flows along the paths that dark matter has laid down. It collects in the gravitational wells that dark matter has dug. It forms stars and galaxies in the places where dark matter has concentrated. But it is not driving the process. Dark matter is. That realization is humbling. We live in a universe where most of the matter is invisible, where the structures we can see are just the tip of an iceberg that extends into a darkness we cannot access with any telescope, any detector, any instrument we have built or can imagine building with current technology. The Great Attractor is a perfect example. The thing we have been chasing for 40 years, the thing that has pulled the Milky Way across hundreds of millions of light years, is mostly made of something we cannot see. The Norma cluster is visible because it contains galaxies. The galaxies are visible because they contain stars. The stars are visible because they burn hydrogen and emit light. But the stars are a minority. The bulk of the cluster, the part that actually matters for the gravitational pull, is dark. A halo of invisible matter wrapped around the visible core, extending far beyond the galaxies themselves, merging with the halos of neighboring clusters to form a continuous web of mass that fills the entire Great Attractor region and beyond. Mapping that web is one of the hardest problems in modern cosmology. You cannot see dark matter directly. You have to infer its presence from its effects on things you can see. Galaxy velocities tell you how strong the gravitational pull is in a given region. Gravitational lensing tells you how much mass lies between you and a distant background galaxy. X-ray observations of hot gas in clusters tell you how deep the gravitational well is. Combine all those techniques and you can build a rough map of where the dark matter is concentrated. But the map is always indirect, always inferred, always subject to large uncertainties because you are trying to measure something invisible by watching how it bends and pulls things that are not invisible. Despite those limitations, the maps we have are striking. The distribution of dark matter in the Great Attractor region mirrors the distribution of visible galaxies, but it is smoother, more diffuse, more extended. The galaxies trace the peaks of the dark matter distribution. The filaments connecting the galaxies trace the ridges. The voids, like the dipole repeller, are regions where the dark matter density is far below average. The correlation between dark matter and visible matter is strong, which makes sense. Ordinary matter follows dark matter. Where dark matter clumps, ordinary matter accumulates. Where dark matter is sparse, ordinary matter is rare. The cosmic web is fundamentally a dark matter web. The galaxies are just lights strung along the cables. The Great Attractor is also a laboratory for testing theories of how structure forms. The standard model of cosmology, the framework that describes the evolution of the universe from the Big Bang to the present, makes specific predictions about how dark matter should clump and how galaxies should form in those clumps. The model predicts that small overdensities in the early universe, tiny fluctuations in the density of matter left over from inflation, should grow over time as gravity amplifies the differences. Denser regions pull in more matter. They become denser still. The process feeds on itself. After a few 100 million years, the densest regions collapse into the first dark matter halos. Ordinary matter falls into those halos, cools, and forms the first stars. Those stars group into galaxies. Galaxies merge into clusters. Clusters link into superclusters. The process continues over billions of years, building the cosmic web one structure at a time. The Great Attractor fits that story. It is a node in the web, a place where the initial overdensity was slightly larger than average, so the collapse happened sooner and more efficiently. The result is a concentration of mass that dominates the local flow, pulling galaxies inward from hundreds of millions of light years away. The structure is still growing, still accreting matter, still merging with neighboring clusters and groups. Billions of years from now, assuming the expansion of the universe does not tear it apart first, the Great Attractor region will be even more massive, even more densely packed with galaxies and dark matter. A fully mature supercluster sitting at the center of a gravitational basin that has drained matter from the surrounding voids. But the standard model also has problems, and the Great Attractor highlights some of them. One of the biggest problems is that the model predicts structure should form hierarchically. Small things first, then larger things, then even larger things. The process takes time, a lot of time. Clusters should not form until the universe is several billion years old. Superclusters should take even longer. But observations of the early universe, particularly from the James Webb Space Telescope, have found galaxies and clusters that are far too massive for their age. Structures that should not exist yet, according to the standard timeline. The Great Attractor is not one of those early structures. It is local. It formed relatively recently in cosmic terms. But the fact that the universe can produce something as massive as the Great Attractor at all, and that it can produce even larger structures like the Shapley supercluster, suggests that the hierarchical formation process might be more efficient than the standard model predicts, or that the initial conditions were lumpier than we thought, or that something about the way dark matter clumps is not fully captured by the simulations. Those are not small issues. They are hints that the standard model, as successful as it has been, might need adjustments. Not a complete overhaul, not a rejection of the basic framework, but tweaks, refinements. A better understanding of how dark matter behaves on the largest scales, how galaxies form inside dark matter halos, how clusters merge, and how that affects the surrounding structure. The Great Attractor is one of the places where those questions can be tested, because it is close enough to study in detail, close enough to measure the velocities of individual galaxies, map the distribution of hot gas, trace the filaments connecting it to neighboring structures, close enough that the uncertainties are manageable and the data is good. Far enough that it represents a significant sample of cosmic structure, not just a local anomaly. There is also the question of what the Great Attractor tells us about the future of the universe. Right now, the universe is expanding. The space between galaxies is growing, carrying them apart at a rate that increases with distance. But expansion is not the only force at work. Gravity is pulling galaxies together. On small scales, inside galaxy groups and clusters, gravity wins. The Milky Way and Andromeda are not being carried apart by the expansion. They are moving toward each other, pulled by their mutual gravity, and they will collide in a few billion years. The local group is gravitationally bound, so is the Virgo cluster, so is the Norma cluster. Those structures are not expanding, they are contracting, merging, growing denser over time. On larger scales, the outcome is less clear. Laniakea is not gravitationally bound as a whole. The expansion of the universe is stronger than the internal gravity. Galaxies on opposite sides of the basin are being pulled apart by the expansion faster than gravity can pull them together. Billions of years from now, Laniakea will not exist as a single coherent structure. It will fragment. The densest regions, the clusters at the core, will remain bound, but the outer regions will drift away, carried by the expansion, lost to the growing voids. The Great Attractor region will survive. It will merge into a single giant cluster, a massive elliptical galaxy surrounded by the remnants of the thousands of galaxies that once filled the region. But Laniakea as a whole will dissolve. That future is determined by the balance between gravity and expansion. And that balance is determined by two things: the density of matter in the universe, which sets the strength of gravity, and the rate of expansion, which is driven by something called dark energy. Dark energy is even more mysterious than dark matter. It is a property of space itself that causes the expansion to accelerate. The more space there is, the faster it expands. Dark energy was discovered in the late 90s when astronomers measured the distances to distant supernovae and found that the expansion of the universe was speeding up, not slowing down as everyone had expected. The discovery was so unexpected that it took years for the community to accept it. But the evidence was solid. The expansion is accelerating. And the only way to explain that is to invoke some form of energy that fills space and pushes it apart. Dark energy dominates the universe today. It accounts for roughly 70% of the total energy density. Dark matter accounts for about 25%. Ordinary matter, the stuff we can see, makes up less than 5%. The Great Attractor, Laniakea, the Milky Way, everything we have been talking about, all of it is a tiny fraction of what the universe actually contains. Most of the universe is dark, invisible, inaccessible. And the part that is not dark matter is dark energy, which is even more inaccessible because it does not clump. It does not form structures. It just sits there, filling space, pushing everything apart. The existence of dark energy means that the long-term fate of the universe is not collapse. It is dispersal. The voids will grow. The filaments will stretch and thin. The clusters will become isolated islands in an ever-expanding ocean of emptiness. Trillions of years from now, Galaxies outside our local gravitationally bound group will have receded so far that their light will no longer reach us. The observable universe will shrink. The cosmic web will dissolve. The structures we see today, the Great Attractor, Laniakea, the dipole repeller, all of it will be memory. A snapshot of a moment in cosmic history when the universe was young enough and dense enough for gravity to carve out patterns on the largest scales. But that is trillions of years away. Right now, the universe is still in its prime. Structures are still forming. Clusters are still merging. Flows are still pulling galaxies across hundreds of millions of light years. The Great Attractor is still attracting. And we are still here, trying to understand it. That is what makes this moment in cosmic history so interesting. We are living at a time when the universe is old enough to have built complex structures, but young enough that those structures are still visible. A few billion years earlier, and the cosmic web would have been too faint, too underdeveloped to map. A few billion years later, and the expansion will have carried so much of it beyond our reach that we would miss most of the picture. We are living in the sweet spot. The era when the universe is most comprehensible, and we are comprehending it, slowly, imperfectly, but steadily. The discovery of the Great Attractor was a turning point. It showed that the motion of galaxies could not be explained by local effects alone. It forced astronomers to look beyond the Milky Way, beyond the local group, beyond the Virgo cluster, out to the largest scales where the cosmic web becomes visible. The mapping of Laniakea was another turning point. It redefined what a supercluster is and gave us a framework for understanding our place in the web. The discovery of the dipole repeller showed that voids are not passive. They shape flows just as much as clusters do. Each discovery built on the last. Each one expanded the picture. The tools are getting better. The James Webb Space Telescope can see farther and more clearly than any telescope before it. Future missions, like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope, will push even deeper. New surveys, like the Dark Energy Spectroscopic Instrument and the Vera Rubin Observatory, will catalogue tens of millions of galaxies and measure their velocities with unprecedented precision. The maps of the cosmic web will improve, the uncertainties will shrink, the flows will become sharper. We will trace the connections between structures across billions of light years. We will map the distribution of dark matter in exquisite detail. We will test the predictions of the Standard Model against observations so precise that any deviation will stand out like a siren. And we will, almost certainly, find more mysteries, because that is how science works. Every answer raises new questions. Every map reveals new blank spaces. The Great Attractor was a mystery for 40 years. Then it became a landmark. Then it became part of a larger structure. Then that structure became part of an even larger pattern. The dipole repeller was not even a concept until a few years ago. Now it is a fundamental piece of the puzzle. What else is out there? What other voids and flows and basins have we not yet mapped? What happens on scales larger than Laniakea? What happens on scales larger than the observable universe? Those questions do not have answers yet. They might not have answers in our lifetimes, but they will be asked, and eventually someone will figure out how to answer them. The Great Attractor is not the end of the story. It is a chapter, a signpost, a reminder that the universe is larger and stranger than we ever imagined, that the things we can see are just a fraction of what exists, that the forces shaping our motion, shaping the motion of galaxies across hundreds of millions of light years, are mostly invisible, that the cosmic web is held together by dark matter we cannot detect and torn apart by dark energy we do not understand, that our place in all of it, our basin, our flow, our trajectory through space, is determined by structures so vast that light takes 500 million years to cross them. And yet here we are, on a small rocky planet orbiting an ordinary star in the outer regions of an ordinary galaxy, riding a current we cannot see toward a destination we will never reach. The Milky Way is falling. It has been falling for billions of years. It will keep falling for billions more. 600 kilometers per second toward the Great Attractor, pulled by the gravity of 10 to the 16th solar masses spread across 250 million light-years. And we, standing on this rock, have figured that out. We have mapped the flow. We have traced the web. We have identified the unseen architects of the universe and begun to understand how they work. That is the story, not the Great Attractor itself, but the process of finding it, of realizing that the motion of galaxies is not random, that the universe has structure, that the structure has a cause, that the cause is gravity acting on an invisible scaffolding of dark matter across billions of years and billions of light years, that we can measure it, map it, model it, and understand it, even though most of it is hidden from view. That is the triumph. That is what makes cosmology worth doing. Not just cataloging objects, not just taking pretty pictures, but piecing together the story of how the universe came to look the way it does, how structure emerged from chaos, how gravity carved out the web, how we ended up here, in this particular basin, riding this particular flow, asking these particular questions. The Great Attractor is pulling, the dipole repeller is pushing, Laniakea is flowing, Shapley is waiting, the Milky Way is falling, and we are watching, measuring, mapping, trying to see the invisible, trying to understand the unseen architects who built the largest structures in the universe out of material we cannot touch and forces we cannot see. That work is not finished. It will not be finished in our lifetimes, but every new observation brings us closer. Every new map fills in another piece of the puzzle. Every new discovery reminds us that the universe is knowable, difficult, yes, complex, yes, full of mysteries, absolutely, but knowable. We are figuring it out, one photon at a time, one galaxy at a time, one basin of attraction at a time. And that, in the end, is what this has all been about. The Great Attractor is not just a place in space, it is a question, a challenge, a reminder that the universe does not hand us answers. We have to go looking for them. And when we do, when we point our telescopes at the darkness and start collecting light, when we measure and map and model until the patterns emerge, we find that the darkness is not empty. It is full of structure, full of motion, full of stories waiting to be read. The Great Attractor is one of those stories, and we are still writing it. So we set out to find a monster, a single massive object hiding behind the Milky Way, pulling 100,000 galaxies toward it with enough force to drag us across hundreds of millions of light years. We wanted a destination, a point on a map we could circle and say, there it is. That is the thing. What we found instead was a process. The Great Attractor is not an object. It is a convergence, a gravitational knot in the cosmic web where filaments meet and matter flows inward from every direction. The normal cluster sits near the center, the densest point, but it is not the engine. The engine is the entire region, tens of thousands of galaxies, uncounted dark matter halos, 250 million light-years of structure pulling together, shaping the motion of everything nearby. And that region is not isolated. It sits inside Laniakea, a basin 500 million light-years across. Laniakea flows toward Shapley. Shapley flows toward something else. The dipole repeller pushes from behind. The web extends in every direction, connecting everything to everything else across distances so vast that the light crossing them carries the entire history of complex life on Earth in the time it takes to arrive. We are not falling toward a place, we are riding a current. A flow shaped by the distribution of mass across scales we can barely map, and driven by forces we still do not fully understand. Dark matter we cannot see, dark energy we cannot explain. A universe where everything visible is a minority, and the structures that matter most are built from things we can only infer. The Great Attractor was never the answer. It was the question that forced us to look farther, to stop thinking in terms of objects and start thinking in terms of flows, to realize that the universe does not have destinations, it has trajectories, and ours, for better or worse, is written in the gravity of things we will never see but can no longer ignore. As new surveys fill remaining gaps, each measured galaxy invites us to see our cosmic home not as a fixed place, but as a current within an immeasurable sea beyond us.